presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. This show is funded by supporters on Patreon and Subscribestar. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody. I hope everyone's having a beautiful day so far. So, as per usual, I need to welcome everybody on down. Now today I have a pretty exciting topic for you. It's one of my favorites. If you want to know some of my favorites, this is definitely one of those. Sorry, I'm just really excited today. Just checking to make sure we got everything here, and I see that everything looks okay. Just going to open up the chat for a little bit. That way can have any discussion. Keep in mind that if you want to partake in the chat or engage, please, just please, we have ourselves a good time over here. If you have questions while we're going through everything, just drop her on in the chat. I have access to the chat for Facebook, YouTube, and Twitch simultaneously. So if you're on any one of these platforms, you can come and engage right in the chat and I will answer your questions. So if you have questions while we're going through the lessons here today, this is the one way to do that. It's really a great time and I like to welcome everybody to do this. So other than that, just a few other things I want to mention just for the sake of completeness before I get started is that if you'd like to support this effort for affordable and accessible computer science educational content, you can find ways to support that on patreon.com/pagewizard at this time. So if you're looking for options, say if you really want to support my work or you like what I'm doing or you want to gain access to the educational materials that come along with all these lessons, that's the way to do it. So just head on over to patreon.com/pagewizard, look at the appropriate tier and see which one makes sense for you. So I have ones just simply for basic kind of donation to say some more basic entry just for supporter access. So for example, if you want to access Discord server and all these things, it's really very low bar. So for example, if you want the materials for today's lesson, it's simply at the supporter access tier. So keep in mind that if you know anybody that's curious about learning about computer science or you're interested, or say you're a university student or a college student, you're looking to enhance your knowledge, or maybe you're trying to find some way of ultimately cracking the code on how to do well in your classes, you're in the right place. Everybody is welcome here. So if you want to learn computer science, I have all the self-learning tools that you're probably going to need to help succeed in that regard. But also if you're looking for just some more resources, you're in the right place. Everybody's welcome. So other thit's I want to mention is that if you really like this content, make sure you subscribe, follow, tell your friends to come on out. I know I have to keep saying that it's one of those things you just sort of do when you're on these social media networks. You just have to tell people this. It's sort of funky how that works. Other than that, a couple other things. Just make sure, of course, if you like what you see, share it. It's a very simple thing. I'm only one guy right here at this time, and I must stress that I'm on the mission to try to really create more affordable and accessible computer science educational content for everybody. And in particular, I'm really big on the idea of trying to make otherwise difficult subjects to access that usually you would have to take an advanced computer science program or a computer science university program to gain access to these materials in the same way I am doing, at least here. Excellent teaching is the way I go here. No mediocre stuff here, but we have a good time here. That's the difference. I'm not going to have a stick shoved up my butt. I'm here to have a good time with you, okay? So regardless, the other point is that, I think that's everything I really had to say. If there's anything else that'll come up, just take a look at the end credits of any one of the videos that I've been putting out more recently, or just simply at the end of this stream. Just check out the links. I consider supporting. If it's because of people supporting my work through these means that I can continue to do this hard work. So likewise, oh yeah, I guess I now remember what one thing I wanted to bring up. So hopefully you're enjoying the content that is coming out. I've been putting out content about 5 times every week, which I'm hoping I can continue to maintain going forward. The schedule of it might change. So right now, presently, the schedule is that I do my live lessons on Tuesday, and then on Thursday, I have a gaming stream. Now, this gaming stream, I'm right now trying to figure out what day works best for people that want to come and watch these streams. So I know that, say on the weekend when I did it the other week, it actually got a lot of more people showed up, which was pretty dang awesome. So either way, that's just some things I'm working out still with the scheduling. But yeah, every week I've been doing a live lecture, which is awesome. This is one of those things I want to do. And of course, if you want to see more of that, let me know. I always want to know what exactly you're thinking about. If there's something that you would like to see, of course, there's all the different ways you can reach out. Comment. Let me know through Patreon. Tell your friends. Tell me in the chat. I want to know about this stuff. So anyways, that being said, let's get started, everybody. So I guess I can... So keep in mind, I will periodically put the chat on and off, depending on, like, basically whenever we have a little intermission between our lesson or there's kind of a question kind of period. Whenever it is not on, keep in mind, I could still see your comments, and I'll try, if they're a very short thing for me to address while I'm talking, I almost certainly will address it. Otherwise, I'll hold off until kind of like this period that we'll have in between each part of the kind of segments we're going to go through here. So anyways... let me just, before I get too wild with this stuff, let's make sure I got a marker that works, because I have this horrible luck these days of finding a marker that, wonderful. Sweet. Okay, this one's good, I think. I might have a dud. So anyways, today we're going to be talking about graphs, and then with the amount of time we'll have, we're going to see what a graph is. We're going to learn some properties of what a graph is. You may know this as a network, for example, and how we can represent these kind of graphs, and also learn about how we can explore a graph. And depending on how much time we have after all of this, I'm going to be doing a little bit of trivia, kind of talking about some kind of nuanced things that are commonly maybe said during a lecture or in a course, but is often not shown to you. So, sorry, there was some random thing just floating there. That was some funny thing. It'll look better afterwards. But anyways, let's start talking about what a graph is. So I think that's a good place for us to start. So the first thing I really want you to know is that graphs a fundamental combinatorial object of much study in the mathematical sciences. So that's like computer science, statistics, mathematics. You should not look at this topic as only just a computer science thing. This is a topic that spans several other mathematical sciences. So just be aware of that. So that means that things that I talk to you about here will hardly cover everything about graphs. In fact, there's so many things I could talk to you about graphs that I could easily just go on for hours upon hours upon hours. And you could take whole courses just on this subject alone, like even just parts of it. That's how expansive, say, graph theory has become over the years. Its earliest roots, you could find a lot of it in, I guess, prior to its advent in computation, a lot of it was done through recreational mathematics. So stuff that people did and were studying interesting things that you can do with graphs. But once you got computers involved, it really became this whole other beast. So I'll give you some examples of how you could represent a graph, just to show you some applications. I'm not really an applications kind of guy, but I most certainly want you to see what graphs could represent. So these are just a subset of many. So a first good place I could start is that you could imagine you have a network. So like a computer network. So for example, the thing that you're watching this video on. So the data that you're getting processed to watch this, especially if you're watching this over the internet, is over a computer network. So this is just a very simplistic picture. By no means is this as sophisticated as the World Wide Web or anything like that. But you can imagine you have some clients, some servers. So the clients are connecting to the servers to gain access to, say, services. Or they might be, for example, just trying to load up a web page, or who knows? Maybe these 3 servers are for like a computer game, and these 3 servers are managing the deployment of communications between players over that network. So suppose that maybe these 2 users are connected to this server. Maybe you have these 2 here, these 2 here, and then say these 3 servers are connected to each other. So this is an example of a computer network. And yes, that monitor over there is getting probably a little too hot. It sort of looks like it's melting. So that's an example of a computer network. So you're going to see that these computer monitors, which are just representing what your computer or some client's computer, and these servers, they got all represent just a single entity in a graph. We're going to see this in a moment. And these connections between them, they're going to form what we call edges. So I'll talk more about that in a little bit as well. So another example is a flight map. So I'll show you just an example of what I mean by this. By no means would I recommend this as just like a perfect model of this, but most certainly this is an idea for how you can represent all sorts of different things. So it's an effective modeling tool for things that have relationships between each other like this. So I'm just going to label out some airports. Whoops, let's make this one R. YVR. Bonus points if you know what the acronyms of these airports are. But what you could do is you can imagine you have flights that go between these airports. So say if somebody wants to go from YYC to YWG, they can take a flight from YYC to YWG. But however, YVR, if I want to go from YVR to YUL, I have to go through another airport to get there. And this is represented by hopping from one of these to the next one. You can look at this like a path. So this route from one airport to another to another. This is what I mean by it being a route map. So these are going to represent the relationships between trips that planes can take from one airport to another. And those people on the aircraft, they can travel using such connections. Hence the literal term connection. So when you hear about like, oh, we have a connecting flight, I'm talking about these. So if you want to go from here over to there, this is an example of a connecting flight. So what I could do is I can even place weights or distances on the edges, these edges that connect them. They can represent, say, the cost of fuel to go from this place to another place. It may, for example, also may represent a physical distance from this to here. So you can use these edges to represent all sorts of different things. So just for the sake of completeness, I'll fill in the rest of this picture so we have an idea. By no means am I saying these are accurate, but they most certainly will be somewhat accurate. One other thing I should also point out is in a graph, more generally, you're going to see that these connections, the way they're organized, doesn't actually have to make any logical sense other than that they're connected to each other. So it's the connections between what we're going to call vertices or nodes, these circles here, or in our example, airports. These are the relationships between these in terms of their connectedness, so how connected they are, or if they are connected, or what matter when we talk about a graph more generally. There's more specific cases when you're studying graphs where the actual drawing of the graph might actually matter. But for general graphs, that is not actually the case. So it wouldn't have mattered if I put y, y, z up here. It wouldn't matter if I put y, w, g over here. It doesn't make any difference. The connections between them that matter. So you're going to see that very often when I draw these. Even if I were to assign, say, distances or anything like that to these edges, it doesn't make any difference. Hopefully that is clear. 2303. Let's go 3,222. Yeah, that sounds about right. And we'll say 4,184. I think I got all the edges. I think I got them all. So this is an example of flight routes with distances. So you can see if ever I wanted to, say, find the shortest route from, say, YVR to YHZ, you can look at these distances and try to figure out what pathway or which sequence of connecting flights gets me from YVR to YHZ. So you can see, for example, there's at least one way to get there. So you can, say, go from YVR to YYC to YUL to YHZ. But keep in mind, that may not necessarily be the shortest one. So I'll let you think about that. So that's something that maybe in future I'll talk more about, is computing, say, the shortest pathway from one airport to the other. So these are two example applications to help you give you a flavor for this. But like I said, it's the connections between these entities. So in this case, these were airports, or in this case, they're computers. It's the connections between these computers that really matters in a graph. So while you see servers and clients, which sure you can represent more information with these if you knew, like this is like a type 1 computer, type 2, or whatever it might be. Fundamentally, when we talk about a graph, you can have that extra information, but ultimately for studying the graph itself, which I'm going to define shortly, what matters when you look at this graph here, because this is really just a graph. It looks something instead like this. So you have, really, I'm just going to reduce it down to the connections between them. Right? So those are all the connections between the computers, right? So each one of these I can label. So I could call this one V1. I'll call that V2. This may be V3. Let's say that's V5, V6, that V4, V5, V6, V7, V8, V9. These may have different labels on them. That's an example of a labeled graph. So these labels may correspond to indices. So how you represent the graph may help you kind of label what they might be like this. But right now we're working at the level of this concept of a graph. It's these interconnections between entities. So we're going to call these entities nodes or vertices, singular vertex. And these connections, these are going to be dictated by what we call edges or an edge. And depending on what the relationship the edge has, we have somewhat different terminology for it. So we're going to talk a little bit about some terminology in relation to this. So hopefully that's pretty exciting. I'm pretty excited. Hopefully you guys are excited. So let's head on over here and let's define what a graph is. So I must stress that there are several ways you can write the same definition down. But let's talk about what a graph is. So at first it's going to sound a little abstract if you've never seen this definition before, but I'm hoping that I'll be able to encourage you to see really that you already know what this is. It's just that I have to write it out a little bit more formally for you. So it's going to be a pair, capital V, capital E, where capital V, or I'll just call it V, is a set of vertices. So those entities that we've been talking about, like the things like, say, those airports over there or the computers over there, these are examples of vertices. So the servers, clients, those are just computers. Same idea. Those airports, they're all just entities in the relationships that I have here, and these are what we call vertices. Sometimes they're called nodes. I must stress, this is a common mistake students make, is they say, when I tell them the singular of what vertices are as just a single one, it's often a common mistake to pluralize the singular. So let me explain. So the singular of a vertices is vertex. So you may have heard of this word from geometry, for example. So it is not, the plural for vertex is not vertexes, it's vertices. It's one of these fun words. So please, just for the sake of me, just please don't say vertexes. It just gets so weird. So sometimes it's a set of vertices or nodes. And capital E, which I'll just call E, is a collection. It's a collection of pairs. Pairs of vertices. Which more broadly, I'll just write like this. With rounded parentheses, UV like this. But I must stress that you can impose extra meaning onto what an edge is, which I'm going to talk more about in a moment. Called edges. Sometimes these are also called links. It often depends on kind of the context you're talking about it. Or arcs. So for example, when the edges form just a singular direction in the relationship. So one entity is only related to another one, but not the other way around. Sometimes the word arc is used selectively in that regard. So one other thing is think of convention for our discussions here. Just also abbreviate some discussion here. So just some convention I'm going to be using is that the number of vertices in a graph, that looks like suspiciously like an E. I'm gonna fix that. Number of vertices is, which we can denote with the cardinality sign, which this means the number of elements in this set. We're gonna write that as n. So n is going to be the number of vertices, and the number of edges in the graph, which you can denote with the cardinality, or the size of E, which is just the number of pairs there are, with M. So this is the convention we're going to follow. So I thought we'd do one, so just to really illustrate this point, just to re-emphasize it, because I think it's really important for us, is say, for example, in our application over here with the route map here, our flight routes. So the set of vertices here would be your airports. So each one of those, there'll be a one vertex. And say, for example, like we have a connection between YUL and YHZ. This would, for example, say YUL, YHZ would be an edge in this graph. So, for example, YUL, YHZ, that's an edge in this graph. So we'll call this, for example, an undirected edge, because you can go from one way or the other way. Now, maybe there's a much more robust model, for example, that may have multiple relationships encoded that only have one direction or another, which sometimes happens with some airports, by the way. Sometimes they have it where a route only goes from one airport to another, but not the other way around. For example, you can think of international flights. Sometimes there's only, like, they only return from a place, but they may not go to that place. You may have to go through a couple other places to get back there. Say, for example, if it's about reducing costs. Let's draw a picture. I think it's important that you see pictures. Pictures, pictures, pictures. I'm just going to draw with this graph. I think it's a pretty cute looking one. The one thing I will tell you up front is that graphs can be really pretty to look at. And I'm going to try, with how much time I have here today, to kind of expose you to just maybe some different kinds of graphs. But I could easily go on and study all sorts of different kinds of graphs based on the relationships they have with each other. So here's an example of a graph. I've labeled the vertices with these alphabetical letters, but that isn't necessary at all. These could be numbers. In fact, technically a graph doesn't even have to have labels on it for the vertices. But this is important that we have some way of knowing which vertex is which vertex. So you can think of these as the names of the vertices. Otherwise, I would usually call them like V1, V2, V3, V4, because the labels don't really matter a whole lot. So here's just an example. So in this case, if this is graph G, then if I say graph G is equal to VE, this would be where capital V is just going to be the set A, B, C, D, E, F. If you're not familiar with these squiggly curly braces, they just simply, this is notation to say, hey look, all of these are a part of this set. The order I write these out doesn't matter, just to be very clear. So it could have been just like F. I could have wrote these all backwards if I wanted to. It doesn't matter. As long as they're present inside of the set. E, well, this one, it's going to be a collection of, now, one thing I want to point out is that I brought this up, is that you can have different kinds of edges. So you can have what we call directed edges, you can have undirected edges, you can have things called mixed edges. There's all sorts of different kinds of edges that can exist for a graph. So in this case, I'm going to write them out in the way I will shortly for an undirected graph. So you'll notice that, so when I talk with directedness or a directed graph versus undirected, what I literally mean is I'm gonna like draw arrows on these, meaning that you can kind of only go in one direction. So if I want to go from A to B, if I put an arrow on here, this means I can go from A to B, but I can't go backwards. So let me write out these in the sense that I will very shortly for an undirected edge. So notice there's no arrows or anything I've drawn on these. There's no sense of direction on the edges, hence its name. So I can have A, B. So note that if you really don't like this syntax or notation, you're welcome to, for example, just use rounded parentheses like I wrote over there. You can write that just right here, and it doesn't make any difference. Just the point is that the order in which I write them does not matter if it's what we call an undirected graph, which I'm going to define shortly. So AB, AC, AF, AE, BD, CD. Man, I could go for some music. And we got DF. So here's the graph. So notice that in our case here, notice that I have AB because there's this edge right here. I have AC, notice that edge is right here. AF, right there. AE, right there. BD, where's BD? Ah, there it is. It's right there. It's right there. BD, we got CD right there, and we got DF. That's all the edges, right? So this is how I could write out a description of this graph. So sometimes it's helpful to draw a picture to show somebody what the graph looks like. It may be helpful to describe it in this form. This is the formal way you would write it. This is the informal drawing. So sometimes drawings are going to be very helpful to understand what's going on with a graph. So let's talk about this whole edge business now. So let's talk about what because I talked about this idea of a directed edge, undirected edge, like what does that mean? So let's kind of talk about that now. So you're going to see that I'm sort of going to unpeel a lot of what we just talked about here. I also brought up this idea of connectedness. So like what does that mean? So we're going to talk about that too. So suppose we're given an edge, E, which is going to be, suppose it has these two vertices as its pair. Suppose it has those as its pair. What I would say is that U and V are endpoints. Are endpoints or end vertices, which it's not as common as the first of these two, but I've seen it used before. End vertices is two words of E. So these would be referred to as the endpoints of E. So if ever you want to talk about, like, okay, here's this edge, what are U and V? They're the endpoints. So you can think of it like almost like if I picked up one of these edges over here and I just like picked it up like this, like a dumbbell. I'm just trying to like lift it. I want to know what vertices are on the two sides. They're the endpoints. So I must stress that there's different edge types. So let's talk about edge types. You're going to find that the former is far more common than the latter, at least when we talk about graph theory. So keep in mind that keep in mind that when people describe graphs to you, they're very often going to talk about just a concept of a graph. Usually when they say stuff like this, they're going to presume the first of these two, almost always, with the exception if they actually just straight up tell you. So just to be clear. So these are just examples of edge types. So you can have an undirected edge. So this is an unordered pair of vertices, U and V. So I must stress that when I wrote out those pairs over there, the reason why I use the curly brackets there is, like I said earlier, it doesn't matter what order you write them in curly brackets like that, or curly braces. This is just a syntax, this is just a way to denote this, is that it's unordered. Sometimes that actually really matters. So this is denoted either as UV with the rounded parentheses. Usually my advice when you use the rounded parentheses is make sure it's clear that you're talking about an undirected graph. So if you define what your graph is, usually a helpful tip I can give you if you plan to use this notation is make sure when you define the graph, say it's an undirected graph. And then this will avoid any confusion about what that is. Or you just simply say it's an undirected edge and then you just give its name like this. So some people will write this as UV with curly braces. Sometimes even people will just literally write UV right beside each other. Just one after the other like this. I find this is far more common in graph theory circles. But I must stress that it doesn't make any difference. UV, it's supposed to be a V. UV is the same as VU. There's no difference between those two. They're the exact same edge. So the fact it's undirected means that it doesn't matter what order you tell me the endpoints of the edge. Doesn't make any difference. This is in contrast to a directed edge. So this is actually an ordered, so this is actually where the order matters with the endpoints. An ordered pair of vertices, UV, where the first vertex, so the first of these two listed, so like example U here, the first vertex U, first vertex U is the origin. Some people call it the origin or the tail of the directed edge. And the second vertex. The second vertex is the destination. So some people call this also the head of the edge. Caution to the wind, if you use the term destination, if you talk about like some routing problem, like our flight map application that we talked about, I would probably not use that terminology because it sounds like you're going to that place. Now, in the context of an edge, as you're going to see my picture just shortly, it's going to be where, like, straight up where if you go from one to the other, if you follow the arrow tells you where you're going, which makes sense why you'd have an origin versus destination in that sense, which could be contrasted with an actual route where you have a pathway from one place to another, which has its origin and destination, which in that case, if it's a directed graph, would be a sequence of origins and destinations, one hop to another to the each vertex. So that's just a little bit of caution from a communication standpoint. And is sometimes called an arc. So sometimes, that M is looking a little suspect there, and is sometimes called an arc or directed edge. So in fact, it would be called directed edge, right? Sorry, I'm getting very excited here. What I'm saying is that some people call this an arc to contrast it with an edge, which sometimes they talk about as just an undirected edge. So the default is an undirected edge. These are more specializations on top that can generalize over this concept. So let me draw you a pic. Actually, one other remark I want to make. So please don't mind. I know this is a lot of terminology, but you'll thank me later. If E is equal to UV, then E is directed from U to V. So that's a very common phrase you'll see. And this is very often abbreviated as U with an arrow V like this. So if you want to give me a sequence of following directed edges, so if you have a whole bunch of them like on our flight wrap, where you want to go from one airport to another, you can almost look at this like a chain of these, if say you have directed edges. This is also one way you can also describe to somebody a pathway, but in directed edges, it's much more helpful as an abbreviation like this. So, let me draw you a picture just to encapsulate both of these points, because I think it's important that you gotta get this all clear. So, an undirected edge, so if we want to talk about an undirected edge, so if you have UV, this is very often how it'll get drawn. You just have a line like this between the two. Keep in mind, it doesn't have to be a straight line, just to be very clear. It could be curved, it could be... It doesn't have to be a straight line, just to be very clear. It's just a connection between the two like this. And this is what UV is. So this is what an undirected edge, or edge, which I'll very commonly just call this an edge, just by default, would look like. This is in contrast to a directed edge or arc, where if I give you, there's actually the order does really matter. So if I give you two cases, suppose I have U and V as the endpoints of the edge. The question is, if I were to draw these two different directed edges, how would I write them? Does anybody have any ideas of how I can write this out? Any ideas at all? So if these are two arcs, just to be clear. So so if you look at this, if you look kind of like at my abbreviation here, it really gives you everything you need to know. So if I give you an edge UV, like this, notice that this is actually this edge right here. So this right here, in our example, I'm just going to kind of draw a box around this to help distinguish it from what's above. This is the directed edge UV. However, this right here, the bottom one is actually the directed edge VU. Notice that it goes from V to U. versus this one goes from U to V. So this is an example of an arc or directed edge. Very interesting, right? Now that we've defined some edge types, now I can define different kinds of graphs for you. So let's talk about this. So once you get a grasp over this terminology, it becomes much, much easier to navigate any discussion about graphs. So kind of the goal of the first part of our lesson here is really kind of to build on some of this terminology so we have an idea of what a graph is, what are some common terminology so you know what people are talking about things, what they mean. Because it's so easy to just talk about lines and dots and talk about things being connected or not. But it would be nice to have a consistent language that we can talk about these things. Now, I must stress that not every graph theorist talks about these terms in the exact way. So if ever it's unclear, you just ask them to give the definition to you, okay? So there's different graph types too. So now that we have definitions for edges, for example, now I can define, for example, different kinds of graph types. I must stress that these, again, aren't all possible kinds of graphs that you can define. These are just some common examples. So I mentioned about the concept of an undirected graph, which very often when people talk to you about graphs, they usually presume it's an undirected graph. Just in the same way when I talk about an undirected edge, people will just call that an edge. So again, just carefully read the context. So an undirected graph simply is a graph where all the edges are undirected. Piece of cake, right? There's nothing too sophisticated about the terminology. It's like, sure, I could say it's not sophisticated, but it's very effective, right? You don't have to, like, if you read this, you're like, okay, that's the definition, right? Like, it seems pretty darn straightforward, right? So naturally, you can have the concept of a directed graph too, which I will tell you that often people will abbreviate this as a digraph. Very often when you talk about directed versions of graphs, they usually like to put this di in front. Not like die, like no stabby stabby. I'm talking di. They'll put die in front of it. So if like some people even refer to a directed edge as a die edge. So this is just simply a graph where all edges are directed. Pretty straightforward, right? At least I hope. Naturally, you can also have a mixed graph. A mixed graph is a graph where edges may be either undirected or directed. So in this kind of representation, the way it would work is that some of the edges will be where you can kind of go back and forth like this, but its meaning is that it's treated like a singular edge, just one edge. This is in contrast to the directed edge, which would force you to have it where, if say like our example with the flight route map, you would have it where you can only go from one airport to another, but you can't go the way around. You'd probably have to find another route. But the point is, in that representation, the way it would work is that you can have, so some routes can only go from one airport to another, but there may be flights that can go back and forth over just a single edge. Now, one thing I do want to mention to you, this is always something that's important to talk about when we start talking about graphs, is I showed you a bunch of different types. Now, there's actually relationships different graph types have with each other, but you also need to remember that a graph isn't just simply just, like, usually when people use graphs, often the important thing is they're trying to model something. So there's some meaning that gets imposed on what the graph is. So give it some formal definition, and it's supposed to represent something. So sometimes the way the edges are defined and sometimes the way the graph is represented can actually make or break actually what you're representing. So let me give you an example of how you can represent any undirected graph as a directed graph. So if I give you a graph that looks like this, very simple graph. This is something that we would call a triangle. See, because it looks like a triangle. It doesn't have to look, it's just three vertices that are all connected to each other. Which I'll have terminology about what I mean by that. So, and when I say that, I'm really saying that if I look at any one of these vertices, notice that they're right beside each other. They're adjacent to each other. Now, I could take this graph and I could actually represent this undirected graph as a directed graph as follows. So what I could do is I can introduce multiple edges like this. So I could take directed edges and I could put them so they go back and forth like this. But here's the catch now. Suppose that you wanted to represent, say, a route that went from this vertex back to itself. Notice that if you wanted to talk about this concept with that graph, it gets lost in the meaning here. You would need a stronger notion of a route or a pathway. So for example, notice that if I try to go here to there, notice that now there's a directed, so if I follow this arrow, which is how finding or navigating through a directed graph would work, is you can follow the arrow to here. But notice now, you don't have to go to that one. You can come right back up here like this. So, but the thing is, it's literally two edges. So if I'm trying to find a way to go from this vertex back to itself, notice that I can go to this vertex and I can go back to myself. Do you see how the meaning gets lost when I translate over like this? So I would need a stronger notion here if I wanted to model the graph like that over there on the right, as opposed to what I have on the left. So this is actually why I'm talking about different graph types, is that sometimes it makes sense to model your problem that you're looking at, or if you're studying a problem on a graph, to understand that sometimes you can lose meaning for what you're actually trying to solve or accomplish by just merely just representing it slightly differently. So in this case, say a pathway, or in this case, what we'll call a cycle, can actually change its meaning from this graph to that graph over there. But it's still a cycle. It's just that we lose the intuition behind what the original graph was doing. A cycle in this case should be, it should be able to go around and come back, right? This is a case of a cycle where none of the vertices are going to repeat each other. So notice that I can still get a cycle over there because I'm still got an extra edge I can use. So anyways, hopefully you found this fascinating. So that is one piece of all of this. So let's see if there's anybody who wants to ask any questions or anything. I'm really happy to answer any questions. So don't be shy. I'm happy to answer anything. So far we've talked about what a graph is. We've talked about what a vertex is, what an edge is. We talked about what different kinds of edges there are. We talked about the notion of if I give you an edge, its endpoints. And we also talked about different kinds of graphs. So just to recap, where we're going to be going from here next is I'm going to talk about the concept of connectedness. So, you know, when I draw an edge between two vertices like this, it's nice to say, oh, these two vertices are connected by an edge. Well, or there's an edge between these two vertices, which sure, you can look at the picture and it's really nice to say that, but I would need some notion of talking about this idea of there being connections between edges, but also connections between vertices. So I would like to have a way of talking about, like, okay, these two vertices, they're connected by some edge. Just one edge. Not many edges. There's not like a pathway or something like that. It's just like one edge. So when I pick up the dumbbell, like I pick up one of these and I look at the two endpoints, I want to be able to tell you that, okay, these two are the endpoints, but I also want to know, okay, well, which one of these, if I picked up any edge, let's say connected to this one by one of these, so there's something between the two, there's an edge between the two, I would like some way of talking about this. So this will be a notion of adjacency, and then we're going to have a notion where, say, for example, I want to talk about an edge, and I want to talk about one of the endpoints, or if I want to talk about two edges, if they're connected by a common vertex. This is the notion of incidence. So we're going to talk about that next. So I'm just going to erase this board on the left. So let me just boogie on over here. Come on over here. Come on over here. We talked about what a graph is. We've talked about terminology. Okay. So now what we're going to do is we're going to talk about this notion of connectedness between edges and vertices. So there's two different notions of this that we're going to be focusing in on. So the first one is the notion of adjacency. So you may say this as the following phrase. So I'm trying to give you a formal way of talking about this so it's not confusing. So there is an edge connecting, and I'm going to use quotation marks around this because we're going to use we're going to have this idea of connected for a graph at some point soon. There is an edge connecting two vertices or nodes. So if I give you an edge whose endpoints are u and v, uv like this, doesn't matter what kind it is, I'm going to break it into two cases for you, is in a graph, then v is adjacent to E is looking a little bit sad here. Adjacent to U. So vertex U is adjacent to U. So I'm going to give you two possibilities for depending on what kind of graph we're talking about, the kind of edge it is, specifically. So in digraphs or directed graphs, V is adjacent to U if you can go from U to V. So meaning you could get to V through U. That's what I'm saying. So I must stress that adjacency in this relationship with directed graphs is not what we call symmetric. It means just saying that V is adjacent to U doesn't mean that U is adjacent to V. Just like we talked about with our picture earlier with edge types, is that you can have an edge that goes from U to V. You can also have an edge that goes from V to U. They have two different meanings. They're two different edges. So you can have the idea of a directed edge, or you can have one that's like this one we had before where we're just like, it didn't matter which direction you're in. For a directed graph, it really matters. So I must stress that this relationship only goes one direction. So I'll say, note it is not symmetric. So that's a little lovely little detail. Maybe we'll put that in the side of our hat or something as a little note, that little pencil, put it behind the ear. So So unless you had an edge that was VU, so right now we only have one that's UV, you couldn't say that U is adjacent to V in a directed graph. However, the good news for you is that it's a lot simpler when it comes to an undirected graph. In undirected graphs, I'll say in undirected graph G, an edge UV. So I'll use the curly braces just to indicate that, oh yeah, it's an undirected edge. But like I said, it doesn't matter if it's curly or rounded like that, just as long as it's clear that you're talking about an undirected graph or an undirected edge. So if this edge is in G, it implies U is adjacent to V and V is adjacent to U. So if we give you an undirected graph, the notion of adjacency, it doesn't matter what order you tell me the vertices. So just as a quick example of what I mean by this, if we had this graph here, suppose I give you this graph. You can say that A is adjacent to B, A is adjacent to C, A is adjacent to D, A is adjacent to E. Notice that there's an edge whose endpoints contain A and some other endpoint. The other endpoint is what it's adjacent to. So you can just look at its neighborhood. So all of our friends here that are connected to A. So we would say that A is adjacent to each one of these. However, A is not adjacent to F. Notice that F, there is no edge where you can see that F is in the same pair as A. Hopefully that's clear. In contrast, if this was a directed graph, something like this, what I could say, if this is the case, so I have A as the first endpoint, and then say, for example, B is the second endpoint. And then I could say, for example, that B is adjacent to A. So notice that I can go from A to B, but I can't go from B to A. So hopefully that is clear. So that's the notion of adjacency. I think it's pretty cute. So I'll have another example in my notes. So that's the first notion of talking about edges and vertices and them being connected. So the second one is what we call incidence. So these are two common ways we can talk about edges and vertices in graphs. So I'll give you another thing to talk about. So let's talk about incidence. So incidence. So you know how in the adjacency we talked about vertices, right? We talked about vertices, those that are our neighbors. You can think of them as our neighbors that we can be, they're connected by some edge to us. Well, incidence is actually, it has a dual purpose. The first one is that it allows me to talk about edges that are shared by a common endpoint, but also if I want to talk about a singular edge and I want to know what one of its endpoints is. So it kind of has two purposes like that. So you're going to see that carefully here. So two edges, E and E prime, are incident. So we would say E and E prime are incident if at least one endpoint. Remember, those are the things that are sticking on the ends of these edges. Those vertices are nodes. At least one endpoint of E and E prime is the same. So very commonly the phrase would be used as follows. E is incident with E prime. You can also say E prime is incident with E if we're dealing with undirected edges. So that's one notion you can use this idea. So another thing I should point out is that you can talk about the relationship one of the endpoints has with an edge using this concept as well. So furthermore, in an undirected graph, edge UV, so if I have two endpoints U and V for an edge, is said to be incident on sorry, I'm getting really excited here. Incident on vertices U and V. So now you have, if you give me some edge E, what you can do is you could talk about the edge being incident on one of its endpoints. So that's very common if you want to talk about an edge and you want to say, hey, look, this edge has this other endpoint. And that's the thing about a reference I want to talk about. This is how you can do it. So I must stress that you can have the notion of incident from and to in a directed graph. So I'll make a remark about this. So in digraphs, an edge UV, so remember it's an ordered edge, so it's directed. So remember it's a digraph, it means it's a directed edge, so this is technically an arc. So just be very clear. I'm trying to expose you to several ways somebody could write this stuff down. So remember this is an arc. So is incident from or leaves. Sometimes people use the phrase leaves vertex U. Leaves vertex U and is incident to or enters. Sometimes people will talk about entering a vertex. Enters vertex V. And that's everything really much about incidence. It's not terribly interesting as a concept. It's useful for language, just like the concept of adjacency. And you can use these two different notions to represent graphs. So I guess for the sake of purpose, I should really just do another example just to kind of illustrate it. I'll use the same graph I had over there. So I'll draw out another graph here. There's nothing special, by the way, about this graph. I'm just sort of just drawing it out. So I have A, B, C, D, E, F. So suppose I pick this edge right here. So first, just be clear, this is an undirected graph, right? Because it has no directed edges in it. So notice that I have an edge. Suppose I look at this edge. Well, I could say that if I call this E, which is kind of confusing because that's a vertex. I'll call it something else. Let's call it Z. So edge Z is incident on vertex A. And it's also incident on vertex B. And also, if I had another edge that shares a common endpoint, say this is edge Y, I can say that Z is incident with Y. Because these are two edges, they're shared by a common endpoint. But I could not say that Z is incident with this edge over here because it's not sharing a common endpoint. They don't share a common endpoint. But I'll let you think about how you would adapt this version for the directed graph. So hopefully you think that's kind of neat. So I have a few other things I wanted to bring up, seeing as I've started kind of creeping in some additional context for how you can formulate graphs. So once we got this, we got the main stuff, the main guts for our graph terminology. Then we're going to see some more. But I thought we would first kind of take a little bit of a refresher after this to learn a little bit more about properties. So at least one property that's very useful when we talk about a graph. It's a very cute but powerful property. Some people call it the handshaking lemma. But first, let's define some additional concepts too. So I'm going to define the idea of a parallel or multi-edge or multiple edge or multiple edges. So these are additional things you can do to a graph to further generalize it. So multi-edges. So, you know when I drew the picture at one point and I showed you, hey, look, you can have like edges. You can have multiple edges that go between two endpoints. You could say that both of these edges are incident on A and B. In addition, you can also even have it where an edge has both of its endpoints being the same vertex. So this example here where I have two edges, two what we call parallel edges or two multi-edges, or these two edges here, and I also have a self loop over there, or some people call that just a loop. So parallel or multiple edges or multi-edges, these are two or more edges. Two or more edges. Two or more edges with the same endpoints. So it's the endpoints that matter here. Likewise, we can also have the idea of a self loop or just loop. Some people call that a loop. One thing to be watched out for is that some people will call also what we call define later as a cycle. They also call that a loop too. So just be careful. So that's why usually I refer to it as a self loop. So it's an edge whose endpoints are the same vertex. So these two edges are examples of parallel edges. This is a self loop. Naturally, once you have these in place, now you can define some more types of graphs. You can define what was called a multi-graph, which is a generalization of a graph. So this is a graph with multi-edges. So it has multi-edges, and typically it has self-loops as well, but it doesn't have to. You have to, like I said, you have to carefully look at how the author is formulating this for you. But usually, this is my experience in research, it's very often a multi-graph will have multi-edges and self-loops. And another thing to keep in mind is the idea of a simple graph. So this is going to be a very common one. So this is a graph with no multi-edges. or self loops. So for example, that graph up there is not a simple graph. However, our example like the triangle, that's a simple graph. All the examples we drew on the board up to this point, they're all simple. So all the undirected graphs I gave you, they're all simple. So I must stress that going forward, if ever I talk about a graph, so please keep this in mind, is if going forward, I want you to assume that the graph is simple. And if I don't say anything else, just also assume that it's undirected. So please keep this in mind. I must also stress that many of the concepts we're going to be talking about generalize over several different kinds of graphs. So just because I'm talking about it as an undirected graph doesn't mean that you can't do it to a directed graph. So just also be keeping that in mind carefully. So just be careful when you're thinking about this stuff. But yeah, this is some basic graph terminology. Fascinating stuff, right? So, are there any questions out there? Don't be shy. I'm happy to answer any questions. Or if you want to just leave me a message or anything, please. I'm happy to talk about it. Or if you just show me some love, okay? It's always a good time. Because guess what? We're having ourselves a great time here. But yeah, no, so we talked about some basic graph terminology. We've talked about what a graph is. We've talked about, like, some people call graphs networks. So just to help you divide over, kind of like hop over a divide. You'll find that a lot of this will be very helpful. See, for example, you're interested in computer networks. You'll find a lot of this discussion here very relevant. It's just that it's often described in terms of computers, not graphs. So just be mindful of that. So a lot of the stuff that we're talking about here is very effective or useful in that context. So another thing to keep in mind, like I can keep going on over and over again. This isn't also just a computer science thing. It isn't just a math thing. These graphs are a powerful tool for modeling. There was a great graph theorist that I knew years back or met before. He always had this phrase that if you had some problem out there, it's almost likely that that problem has some representation as a graph. And I also believe this. For many problems, that you'll find that a graph is a very natural, or sometimes, even if it isn't very useful, there is some way to represent as a graph, usually. So this ranges from, say, if we're talking about like biological stuff, like, for example, representations of relationships, say from on a genetic level to even just zoological level. People categorize things using what people could talk about as graphs. Likewise, chemists, for example, even use molecular models that you can model as graphs too. So the extent of graph theoretic concepts can be useful in several disciplines. Sometimes it's not even really that of a thing that people even talk about in some fields. They aren't aware of this stuff. So sometimes in more recent years, even the past couple decades, you've seen more of a shift towards some of this stuff. Because especially of the computational usefulness of graphs and the algorithms that exist for them for studying underlying structures. Or even just solving basic problems, right? It's good stuff. So the next thing we're going to be doing, before I get into the next kind of segment of this, we're going to talk about our first property of what a graph that we haven't really focused so much on this idea, but it's most certainly something that I'll be focusing in on for this next part, because I want to address two fundamental questions. One, now that we know about the concept of adjacency and incidence, now I can ask the question about, okay, so how many edges are in my neighborhood? So how many other vertices am I connected to? There's an edge between them. If I wanted to have some way of connecting this to the number of edges in the graph, or some other concepts and you'll find that this is actually a secretively but cute property that you can use in all sorts of different settings. And we're going to see one example way that this could actually creep into even talking about a data structure. So the next thing we're going to focus in on is this idea of what we call the degree of a vertex. And I'll give you a classic graph theoretic result that is so easy to prove that you could show a 5-year-old this no problems. And they would understand what you're talking about. If you show them the picture and you show them the argument, I encourage you to play this game, especially if you have kids or if you don't. Say if you have a niece, a nephew, anybody, I encourage you to try showing them this idea for the proof. It's really kind of cute. It's arguably one of the easiest proofs that I usually teach in a class that's on data structures and algorithms. It's like a 2-sentence proof. It's really simple. It's an example of something we call a combinatorial argument, which I'll explain a little bit more about that in a moment. So again, if you like this, make sure you give a thumbs up or tell your friends to come on out. We're having ourselves a good time. And it's only because of people supporting this work that makes this possible. So do check out the links in the description or check out the links on my channel. Find ways that you can share and help out the channel, because I'm trying to get more affordable and accessible computer science education out there at the standard that I think people would appreciate. Hey, so sorry, I'm getting into this. I'm just like in my graph theory zone, man. So we got, let me just see where we're at here. I got all sorts of fun props in front of me, because we're going to be getting into that once we get through kind of the main topics here, because we sort of have, because I'll give you a roadmap for where we're going before we get into the next thing. We got to talk about the degree of a vertex. We're going to talk about this thing called a handshaking lemma. And then we're going to talk about some other graph theoretic concepts, some basic structures that occur in graphs. Then we'll talk about how we can represent a graph. And then we're going to talk about how we can explore a graph. So that's sort of the plan, is I'll talk about some of these things, and we're going to work our way up there. So by the time you're done this, you will have learned at least one algorithm. In fact, I might show you a couple, to how you can explore a graph. I'll maybe show you one application of at least of one of them. I'll have more details in the notes for a discussion. So let's talk about this. Sorry, I'm getting really excited here. Hopefully you're getting excited too. So let me just see. I just want to make sure I don't lose track of anything. I'm a very meticulous person, and I hope you appreciate that. It's sort of one of these small details. Okay, so let's talk about, okay, let me just get us ready here. So the next thing we're going to talk about is the degree of a vertex. So we're going to talk about degrees. I'm not talking about like academic degrees. I'm talking about this thing we call a degree of a vertex. So let us consider the degree of a vertex. So I'm going to give you a definition and I'll give you an example. So here I think is a pretty good starting place. So I'll use one of the graphs I drew earlier. So I have A, B, C, F. I'm just adding those two edges in there. F, C, D, and E. So you might ask, what exactly is the degree of a vertex? So what does degree mean? So very often this is denoted as deg of V. So if I give you a vertex V, deg of V is the degree of the vertex. It is simply the number of incident edges of V, or on V. So for example, let's consider the degree of A. So how many incident edges are there on A? 1, 2, 3, 4, right? How about, let's consider the degree of, say, let's consider D. D's right here. How many incident edges are there on D? Let's see. Let's just count them. 1, 2, 3. There's 3 of them. Piece of cake, right? How about the degree of E? Can somebody tell me that? How many incident edges are there on E? So E's right there. Well, it's just 1, right? It's just 1. So this is what I encourage you to fill in the rest of the degrees of these. So that's what the degree is. You can also define on directed graphs or digraphs the notion of degree, which generalizes over it. So you have this concept of what we call the in degree and the out degree. The in degree is simply the number of incoming edges. So if you look at the arrows, they're pointing towards the vertex. The out degree is the number of outgoing or edges that are leaving. So so if you have your directed edge that goes from one vertex to the other, the outgoing edges are the ones, so if you look at the head of the arrow, the ones where they're not pointing towards it, so they're going outwards, the out degree counts the edges that are leaving a vertex. The in degree counts the ones going inwards, okay? So a natural question is there any relationship between the vertices, their degrees, and the edges? So this brings me to a cute but powerful result. So very cute but powerful result. So often this is called sometimes a degree sum formula, but I'll refer to it as the handshaking lemma. Though the handshaking lemma has a few different characterizations. And people call this the handshaking lemma for 2 reasons. First, a lemma is a theorem, but very often this is used to help you get to the main result. That's why it's called a lemma. Lemma is a special name for a theorem. Handshaking in the following sense. So suppose that maybe I'm at a party or something like that. Perhaps you probably get out more than I do. Suppose that this graph here represents the handshakes that were happening among people. So suppose that person A handshakes E, F, C, and B. You'd agree with me that from the perspective of A, how many handshakes happened? 4 of them happened, right? But if you ask E, how many handshakes did E partake in? 1 happened. There's 1 handshake that happened. Now, this relationship for what each one of the party members, people at the party, will tell you about the handshakes actually has a relationship with the number of edges in the graph. So let me kind of expose this structure to you. So watch this. And this is true for any undirected graph, and I must stress that this result also generalizes over multigraphs. For any undirected graph, the following is true. If I add up all of the degrees over all the vertices, so I'll write this with a fancy sigma notation that says, hey, look, for each one of the vertices, so for each vertex in the set of vertices, so this means n, so I'm saying for each vertex in the set of vertices, I'm going to add up the following quantities. So I'm going to sum over So imagine I went through each one of these vertices, I got their degree, and I wanted to add them all together and throw them in one bin. That's what this represents when a sum is being used. It's summing over the following quantities for each vertex. It's getting the degrees, it's collecting them up in one big bin. This is the sum of all of them. This is exactly equal to 2 times the number of edges in the graph. So let's return back to what I was telling you about when we talked about our story about people shaking hands. Okay. If I were to ask how many handshakes happened in total of all the party members overall, so I ask each one of them and I ask, okay, how many handshakes did you have? Well, let's think about this. Let's think about it. From the perspective of A, they shook E's hand, F's hand, C's hand, and B's hand, right? If you asked any one of them, how many handshakes did you partake in? They'll tell you, oh yeah, I shook hands with A. I shook hands with nobody else, right? F will say, hey, look, I shook hands with A. I also shook hands with F. And that's all F would tell you. C shook hands with A. And shook hands with D. B shook hands with A and with D. And then if you asked any D over here, say, oh, well, I shook hands with F. And I shook hands with C. And I shook hands with B. Okay, so let's answer a question. How many handshakes happened in total if you asked each one of the people at the party? Did you see something very subtle that was happening here? Well, the total number of handshakes that truly happened is actually the number of edges. However, if you asked each party member how many handshakes they had from their perspective, let's think about it. When I asked A, I counted E. When I asked E, I counted A again. Do you see that? So notice I'm doing something that is a common counting trick called double counting. So notice that I am actually double counting each one of the edges. Do you see how a double count can lead to 2 times the number of edges? If I were to be some arbiter outside of this whole party, counting how many times truly, how many handshakes happened, they'd tell you this number of edges. But because each handshake requires 2 people, in this sense, it's you double count it. So hopefully everybody sees that. So let's write out the proof. So this is the argument I was telling you that you can try on your niece or nephew or anybody else. If you want to try out this argument with somebody and ask them how many handshakes happened in total, and you asked everyone at the party and you collect them all up in a bin, they tell you it's actually twice the true number of handshakes that actually happened. So by definition, the degree of a vertex is the number of edges incident on a vertex V of the set of vertices, right? So remember that. That's important. Then what happens? Well, we need to kind of frame this into an actual argument, right? Just saying that, oh yeah, I crossed the line twice, the edge twice, isn't really very seductive as a mathematical argument. So let's do that. So every edge is incident, right? Remember there's that incident concept, is incident on 2 vertices. Incident on two vertices. So by double counting, every edge is counted twice in the sum the sum over each one of the vertices of their degrees. That's the end of the proof. It's very simple. Piece of cake, right? So it's actually one of the easiest proofs that I usually can show somebody. So the whole idea is if you're not convinced by this argument, what you do is you just simply walk through the reasoning we did here. So notice that every time you pick one of these edges up, each one has 2 endpoints, right? So if you count the amount of degree that gets contributed when I look at each one of its endpoints, it contributes a value of 2 towards the sum. Does everybody see that? Very cute. Now, I mentioned as a remark that this also generalizes to multigraphs. That includes when there's self-loops present. One thing I need to point out is that a common convention is that if you have a self-loop contributes 2 to the degree of a vertex. If you accept this, where you can imagine you add a given vertex and you look at my 2 endpoints. Well, from one endpoint, it's the same one, right? But from the other endpoint, it's the same one. So if you actually think about it, it's okay, well, I'm really incident on myself, but at the same time, I'm also myself. So if you accept this convention, this argument can be easily generalized. So notice here that it's incident on 2 vertices. Notice I didn't say anything about them being distinct either. So if you accept this, this proof also generalizes to multigraphs. Because there's nothing saying that if you have parallel edges in the graph, that it changes anything about what we just said here, because it's the same idea. You'll just have 2 parallel edges. That means the party members just shook hands multiple times. So if I pick 2 party members, they would just tell you, hey, look, I shook this guy's hand twice. So one thing also I want to point out for the sake of completeness is that you can also argue that this handshaking lemma also applies in the sense of directed graphs. What you can say there is actually that the sum of the in degrees is equal to the sum of the out degrees. So meaning the arrows pointing in, if I count up all of those, and I count up all of the ones going in so I count all the ones going out, going in, they should equal the number of arcs in the graph. Sorry, I'm getting very excited. So that's a remark I'll give you here. Now, I want to bring this up into another sense here. So the next thing I would like to do is talk about this idea of a complete graph. So let's talk about a complete graph. So ultimately, by the end of this part here, I'm trying to address one question. If I give you a simple graph, what's the maximum number of edges it can have? And the answer will be given to us by a complete graph. So what is a complete graph? So a complete graph on n vertices which often in the literature is denoted as follows. It's denoted with a capital K with a subscript n, is an undirected graph. It's an undirected graph where every vertex is adjacent to every other vertex. So I thought I'll give you some examples of what these would look like for given numbers of vertices. So you can start off with just having one vertex. So this is the complete graph on one vertex, just a single vertex. The complete graph on two vertices just looks like this. Looks kind of like a little tiny dumbbell. Just I pick it up. Do some weights with these. So I got K2 here. What would this be? So if I give you three vertices, well, that's K3, right? And we actually had another name for K3. K3 is also known as a triangle, or a triangle graph. And also you can have K4. So there's four vertices. Each vertex is adjacent to every other vertex in the graph. So I have K4. Like I said previously, by the way, you can also draw these graphs somewhat differently, right? Like it didn't matter that this vertex was right here, right? It could have been drawn over here. Likewise, I could have easily taken this vertex, drawn it out over here, and gotten something else like this. So notice that this is actually no different than the following. So notice I have four vertices. Every vertex is adjacent to every other vertex. But notice it's still the same graph. So more generally, you can take to build any one complete graph, you just simply start off with, say, your first vertex, second vertex, you connect all the vertices. So notice it's like K1 going to K2. I introduce another vertex, you get K3. I introduce another vertex. I get K4. I believe I got all of them. 1, 2, 3, 1, 2, 3. One way you can check, by the way, is if you notice that the number of incident edges, the degree of all of these vertices will be exactly n minus 1, where n is the number of vertices. So if you see 3 always going out of these, then you're all good. Then you can keep going with this. So you can keep... So for an arbitrary kn, you just keep doing this process. The point is that if you ask how many edges the complete graph has, you get something interesting. That all comes back to the degree of a vertex. How many edges does kn have? So let's look at each one of the vertices then. Let's look at the degrees of those vertices. Because if you want to ask a question of how many edges there are, well, the handshaking limit gives us information about that, right? If we sum up all the degrees, it's exactly equal to 2 times the number of edges. So we actually get an important ingredient for finding out how many edges there are. So let's think about it. So for every vertex I'm just going to go through each one of the vertices, just like my picture over here. 3 all the way up to n. Vertex vi is adjacent to n minus 1 other vertices, right? But what does that mean? It means that the degree of each vertex is exactly equal to n minus 1, right? So you can come at this, answer this question through a couple of different means. In the notes, I'm going to show you how you do with double counting, which is just going to be the same argument I gave over here. But notice very quickly that, okay, well, if the sum of the degrees for all the vertices in the complete graph on n vertices is equal to n minus 1, then it's simply this. Well, for each vertex, well, what's each vertex? Well, each of them has a name, right? vertex 1, vertex 2, vertex 3. There's exactly n of them. So I'm going to sum over from I is equal to 1 to n, because I've used these names over here. Keep in mind that it doesn't matter. It's just the thing is that there's exactly n of them. Each one of these is n minus 1. But what is this? Well, I do this n times, right? So I'm collecting n minus 1 up into a bucket, and I do this n times, right? So suppose I have a bucket here. This is n minus 1. I put it in the bucket. I would do this exactly n times. So if I have n minus 1 and I do this n times, how much should I have in total then? Well, it's n. I do it n times, so I add n minus 1 n times. So I have n times n minus 1. But the handshaking lemma tells you the following information. So by the handshaking lemma, sorry, my writing is just melting here. By the handshaking lemma, that would mean that n times n minus 1 is exactly equal to 2 times the number of edges. Well, if you can remember back how do you do algebra here, you can divide both sides of this equation by 2. So this is no different than me writing that m is equal to n times n minus 1 over 2. So I'm going to divide 2 on both sides of this equation, and thus we get the number of edges. So another way you can derive this is through the same kind of double counting we just did over here. So that answers our question of how many edges there are in a complete graph. Very fascinating. So as a consequence, notice that for any simple graph, you can't have more edges than this. So that means that if you wanted to answer the question of how many edges can there be in a graph, the complete graph gives you that answer. So let's talk about that. Okay, so anyways, so here's a theorem for you. So for any undirected graph, so remember I'm presuming that it's simple. The number of edges is at most, so it's less than or equals to n times n minus 1 over 2, which, if you know your big O notation, this is big O of n squared. So you can actually answer a very similar question for directed graphs. So do you notice that earlier on when I was talking about graph types, I talked about how you could take any undirected graph, turn it into a directed graph. Did you notice that I could just simply replace each undirected edge with 2 directed edges, right? So notice that you get twice as many edges, but they're all directed edges. So notice that you would just drop this 2 here. So the divided by 2 goes away because we're not double counting anymore. They literally are there. So you can also say in that case that the maximum number of directed edges is big O of n squared. Fascinating, right? So isn't that neat? So you can see that how we can use simple things like the handshaking lemma to help us argue things like the maximum number of edges that could be in a graph. So let me see if there's any questions or anything. So please don't be shy to ask questions. I'm happy to have it. Please just tell me if you have anything that you just you're dying to know about when we talk about like the degree of a vertex or the handshaking lemma, or if there's anything you want clarifications about, I'm happy to do that. Or just let me know what you're thinking. So let's so the next thing we're going to do after this little intermission is we're going to talk about paths, cycles. We're going to talk about the notion of a tree, like what a tree is. And we'll talk about the idea of a subgraph. And we'll talk about this. So you know how I told you earlier on about this idea we're going to talk about connected, like what that means? I'm going to give you a definition for that. For the purposes of time, I'm just going to keep it strictly to undirected graphs, but I will have some more details in my notes. These are going to be available on Patreon, patreon.com/pagewizard. I'll have them available shortly after this stream. And once we have that, then we're going to talk about how we can represent a graph. So I'm going to go over that a little bit more at a higher level. And from there, I'm hoping that I'll show you at least one graph traversal algorithm. I think that's a pretty good place for us to stop. We'll see how much time we get, because time just kind of goes by when you're having a good time, and hopefully you're having a great time learning. So before we get to our next kind of chunk of things we're going to talk about, because like I said, by the time, like I promised you, by the end of this, you're going to learn about how you can explore a graph. So I'm going to give you at least one way to do that. Maybe if you guys really like it, or anybody likes it, I can come back and talk about more ways you can explore a graph. And also I'll talk about some more graph algorithms. So I'm just going to erase this other board, because once we get this out of the way, it saves us a little bit of time later. Okie doke. Let's see where we're going next here. So I just want to make sure I'm not keeping around things I don't need to keep around, because I got a lot of things to play around with here. So let's see. We got paths, cycles. Okay. I think we're good to start. So let's get in on this. So the next thing we're going to talk about are some more graph terminology. Sorry, I'm just getting very excited here. So we're going to talk about some more graph terminology. I'll try to razzle it up with some properties in between. So hopefully this will be helpful. Terminology. We're going to keep this simple. I've been having a little bit of a long day here. More graph terms. Hopefully you'll appreciate it. It's less writing. So we're going to talk about some more graph terms now. So I'm going to kind of revisit some more concepts, things I've alluded to near the beginning of our lesson. So the first thing I'm going to define is something called a path. I must stress that some people have different terminology for some of these things. So be warned, I'll try to give you some tips on how to distinguish between the two. But a path is simply a sequence of adjacent vertices. And some people call this a walk, to be very clear. So a path is simple. So some people call it a simple path. It's simple if all the vertices are distinct, meaning that they don't repeat. So one thing I want to bring up as an important remark is some people will refer to this as a walk, and some people will refer to the latter as a path. It's very common that when you talk about a path, usually it's this case that it is simple, but just be very careful and make sure you read carefully what they're talking to you about, if you need to know that distinguishing remark. So a path might mean just simply a sequence of adjacent vertices, or it might be a simple path if no vertices repeat each other. But you'll find in a lot of CS circles that the latter part is what people call a path. It's usually just presumed to be simple. So let me give you an example. I'm just going to draw out a graph here. So I'm going to draw something called a wheel graph. So you first start off with something called a star graph. They call it a star because you have a center to it, and then it has rays that go out of it, like a bright sun, you know, like a star, twinkles. So this is a star graph, and what I'm going to do is I'm going to make it so it looks like a wheel. So I'm going to add an outer perimeter, a pathway around the outer perimeter. This is what we call a wheel graph. So this is an example of it's just a graph, remember? So I'm just going to give these names. So V1 is going to be the center there, V2, and then I'm going to go around V3, V4, V5, V6, and V7. So suppose that I were to take some pathway in here. I'll include some other examples in the notes, but suppose I go from V7 to V2, down to V3. This is a path, right? Like V7 to V2 to V3, right? So I have V7, V2, V3. There's a path for you, right? It's a sequence of adjacent vertices. If I were to tack on V5 right after V3, is it still a path? No, right? It's because V5 is not adjacent to V3. But is this a simple path? Yeah, it's simple. Notice there's no repeating vertex. However, if I continue this pathway, I go to V1, then I go to V2, and then I go back to V7. Is that a simple path? No, because I've now repeated V2. So I must stress that you can also define for a directed graph a directed path. In that sense, you have to follow the arrows. So if there was an arrow, say from V7 to V2, then you can follow that arrow in your directed path, but you cannot go the other way around. You actually have to follow the arrows. Just think of it like you're going on an obstacle course, but you're only allowed to follow the arrows. You have to follow the arrows. You can pick a direction to go in for your path, but you cannot go backwards on an arrow. That's the notion of a directed path. So it's also a concept of a cycle. So it's a sequence of adjacent vertices. So you know it's a path, right? But the first and last vertex are the same. So some would call this a closed path. So it means that you're taking some trip in the graph, but you have to, wherever you start, you end there. So for example, let's consider going from V6. Let's go V6, V7, V1, V6. This is a cycle, right? It's a path, but notice the start and end are the exact same vertex. So in this case, V6, V7, V1, V6, this is a cycle. And likewise, we can also define a simple cycle by the same rules. So it's called simple if no repeated vertices. Except for the last two, right? In particular, it has to be that these are at the start and end. You can't have it, for example, where it's just like somewhere going back to the start or the end, in between somewhere. It has to, what I'm saying is that you can have it where you can go from V6, V7, V1, V4, V5, V1, and then back to V6. That is a cycle. However, it's not simple because I repeated V1 twice. But notice V1 is not the start or end of the path. So these are the notions of a path and a cycle. You can also define the notion of a directed cycle on a directed graph by the same concept. So that being said, we're going to talk about some more structures that can exist with graphs. So let's talk about this. So you may have heard of this concept. If not, that's okay. Of the concept of a tree. Now, I'm not talking about trees outside. I'm talking about this notion of a tree that sometimes appears in some data structures classes. It's a very powerful concept because there's a lot of things we understand about the graph theoretic structure of a tree. Trees. So next we're going to talk about trees, forests. We're also going to talk about subgraphs and connectivity next. So first I thought I would start off with the last one, like what it means for a graph to be connected. So a graph is connected so we say a graph is connected if there exists a path from each vertex to every other vertex. To every other vertex. So for example, is this graph over here connected? I'll give you a moment to think about it. Well, let's look at any one of the vertices here. So I pick off V7 here. Well, V7, notice there's a path from V7 to V2, right? Through this edge. We can take that path. There's several other paths too. I can get the V1, I can get the V6 directly. They're part of my neighborhood. We're up in here, okay? So then I could also get the V5. For example, I'll take this path. I can also get to V4 from this path. That's one possible path. The point is that it exists, right? It has to exist. Having multiple paths doesn't make any difference here, as long as at least one exists. Also, V7 can also get the V3. You'll notice that each one of these pathways I can also take to go from that vertex to V7, right? Does everybody see that? So you can make arguments similar to this, but you can check each one of these vertices against every other vertex, and you can see that this graph over here is connected. It's an example of a connected graph. So that's an example of a connected graph. So this graph over here is connected. Now, you might naturally ask, okay, so what does it mean if that is not true? So suppose that I had another vertex. Say V8 over here, and I have another vertex, V9 over here. Suppose there's two vertices. They have an edge where both their endpoints are V8 and V9. Notice that there is not a path from V8 to V7, nor is there a path from V9 to V1, for example. Either one of them, or even it could have just simply been V8 just sitting out here by themselves. Maybe they're just enjoying the rest of their day, having a relaxing time. This would not be a connected graph. We would say that this graph is disconnected. So there's no path here, right? There's no path to V1. This would imply that this graph would be disconnected if you had this happen. Because there does not exist a path. So naturally, when you have a directed graph, you can have a stronger notion of connected. So I'll put more details in the notes about this, but if you have a graph like that, when you start imposing directed edges, so if you have directed edges in your graph, there's two different notions. There is the structural property of an edge. I was about to get physical about it. If there's simply an edge where its endpoints are the vertices, then it doesn't make any difference if it's directed or undirected. So there's this notion of connected as in the sense of an undirected graph. This is called weakly connected in a directed graph. And then we have this other notion called strongly connected. That is where there literally has to exist a directed path from one vertex to every other vertex. And this has to be true for every one of the vertices. Just like this, except you replace everything we talked about with a path with directed path. So that's the notion of weakly connected versus strongly connected. Strongly connected requires you just take this definition, you put directed path right here. In a directed graph, if you want to just talk about weakly connected, you'd use the same definition here, except you take every directed edge, turn them into undirected edges. If there's multiple edges, you just contract them into a single edge. So you just flatten those parallel edges into one edge, and then you ask the question. So I'll include an example of what I just spoke about here. Now, the next thing I'm going to talk about is the concept of a tree. And I must stress that there's many definitions of what a tree is. So I must stress that you're going to look at my first definition. If you ever learned about trees before, you may have gotten a different definition. So I must stress that there's more than one. So a tree is simply a connected graph with m, remember m is the number of edges. It's going to have m is equal to n minus 1, where n is the number of vertices. It has this many edges. So where m is equal to n minus 1. But I must stress that there's several other ways you could define a tree, and all of them are useful in their own ways. I must stress that there's probably some graph theoretic proofs out there that will use one characterization of a tree, or even combine these to help you. So you'll start off with saying, oh, okay, there's this is what a tree is. And then you might use one of these alternate definitions to invoke a property. It's very common. This is also one of the reasons why trees are so useful when you start talking about data structures. There's a lot of things you could say about a tree. So any two vertices, so this is one thing, any two vertices in the tree, G, are connected by a unique simple path, meaning that you can take any two vertices in the graph and there is a unique simple path between them. So that's another way you can equivalently define a tree. So you know right away the thing sitting behind me right here, that is not a tree, right? Because just keep in mind, I haven't drawn you what a tree looks like what a tree can look like. So notice V2, notice I can go to V7 by just going through this edge, but I also could go to V1, then go to V7. So you know right away this is actually not a tree. You also know right away it's also not a tree because it has too many edges. It's connected, but it is not a tree. Another way you can also define a tree is that G is connected, so our graph is connected. But if any edge is removed, the resulting graph, which I'll call the induced graph, so this is the graph that you get as a result of removing this edge, the induced graph is not connected. So removing any one edge in the graph will disconnect the graph. So you clearly see you can't do that to the thing right behind me. You'll find another pathway. Now here's another one. This also will give you some helpful insight in what a tree will actually look like. G is acyclic. This means it contains no cycles. So if you're looking at what acyclic means, just look at the word. Cyclic. If the graph is cyclic, it has at least one, it contains at least one cycle. If it's acyclic, it means the absence of a cycle, right? So there is no cycles in this graph. And the number of edges is exactly equal to n minus 1. So it's acyclic, and the number of edges is exactly equal to n minus 1. And I think technically it also, let me think here carefully before I get too excited here. Okay, it's acyclic, and it has that many edges. Now, one thing I guess we technically have to be careful about is it's also connected, right? Otherwise, you could have it potentially where there's, like, let me give you an example of what I mean. So notice here I have, actually, no, I think we don't need that constraint. I'm just having a bit of a brain fart at the moment. We would need enough edges to get this all across. So keep in mind when I give this definition, it's actually simple. I was just thinking to myself, as I was thinking it through with you, that, oh yeah, no, well, this could represent another definition that we have, but actually, no. It's actually, because notice that if I had it work this, then I don't have enough edges. But if it's a simple graph, then you're okay. So let me just erase that over here. So a third alternative definition, so a third alternative definition is that G is acyclic and the number of edges is exactly equal to n minus 1, where n is the number of vertices. Now, keep in mind that there are some other things you can do with a tree. So note that for any tree, if you try adding an edge to it, then what happens is it actually creates a cycle. So I'll show you with the example in a moment. So that's also an actually handy property that you can think about for a tree. Sometimes it's important that you can tell the difference between what a tree is and what isn't a tree. One thing you can do to any one tree is that if you add an edge to it, its resulting graph will have a cycle in it. Have at least one. So let me draw you a picture of a tree. Okay, so let's see here. So here's an example of a tree. Here's a tree. Notice that you can pick up any one of the alternative definitions or my definition over there, and you can apply it, and you can check that this is in fact a tree. So you notice that there are no cycles in this graph. But notice that if I were to add, say, an edge right here, notice it actually creates at least one cycle. It'll create one right here. And also count the number of edges. I have 1, 2, 3, 4, 5, 6, 7. I have 7 vertices. The number of edges is 1, 2, 3, 4, 5, 6. There's exactly one less. So notice that if I were to include one extra edge, you know it's going to be connecting another pair of vertices that already have some edge on incident on them, but it's going to create a cycle like we talked about. But also notice that if I try to remove any one edge in this graph, notice that if I take this edge out, notice it disconnects it. So then these vertices can't reach those ones over here. So that's what a tree is. A forest, however, is a set or collection of trees. So suppose you want just not one tree, you want many of them. A set or collection of trees. So I must stress that for any forest, the relationship between the number of edges versus the number of vertices is always going to be m is less than or equal to n minus 1. This is actually something I may have mentioned at some past point, where if you bound the number of edges, there's some possibility, there's some freedom for how the edges may connect with the vertices. So you'll notice very quickly that if I remove this edge, I end up with actually 2 trees. Do you see that? This would be an example of a forest. It consists of 2 trees. So for example, here's a cute example of a forest. Drawing the pretty pictures. So there's 1, 2, 3 trees here. This is just one vertex, but it is still a tree. This is actually, some people would call a single vertex like this just an isolated vertex. Because it's sitting out there by itself. It's all lonely. It's isolated. Make sure you spend some time with your isolated vertices. Okay, everybody? So next we have this idea of a subgraph. So it's just simply a subset of vertices. A subset of vertices and edges that forms, as a result, a graph H. So just some other graph. So you're going to take some parts of the vertices and edges. As long as it forms a graph, we could call it a subgraph. So for example, if I give you this lovely picture of a graph, I'm going to start off by drawing its outer perimeter. And I'm going to connect all of these vertices. Finally, I'm going to do one of those tricks that, at least when I was a kid, like people used to always doodle these all the time. I'm going to draw a star here. I promise I'm not trying to summon the occult or something here. We're not getting some superpowers here that are super epic or something that listen, my point is if anything that after watching this, you're after there and you're having some bad luck, please don't blame it on me, okay? So I'm just having a little bit of fun with you guys, okay? So notice that if I omit the edges that are all incident on these vertices, I end up with the star here that's in the middle. So for example, a subgraph here would be if I take these 5 vertices and all of the edges that connect these ones. So if I take all of these edges, I end up with this graph right here. So if this is G, this is my subgraph H. Do you notice very quickly that I can't just simply just like have a dangling endpoint on an edge? Like remember, an edge consists of a pair of vertices, right? You can't have it where like there's no vertex here. It has to be that there's a vertex there. That's why when I say it forms a graph is very important. You can't just take any subset of these edges without including the vertices that are necessary to have those edges. So one thing I'm just taking a moment just to think about this. One remark I can make is that some people talk about the notion of an induced subgraph. That is where if you take a subset of the vertices, so you take some of these vertices, and you ask, okay, so what would be the graph if I only included the edges from the original graph that are present only with those vertices in place? That's what we call an induced subgraph. So one last thing I'm going to define here before we get into representations is the idea of a connected component. Now at first, this is going to sound a little bit weird, so please just stick around with me. So connected component. So I'll first write out a definition for you, and then we'll kind of dissect it. A maximally connected subgraph. So there's a few things that are in here that we've learned that I want to kind of put together with this new word. So first, we know what a subgraph is, right? It's some subset of the vertices and edges that form a graph. We know it's connected, meaning that we know that there's a pathway that exists between any pair of vertices I pick in that subgraph, I guess. And then there's this idea of maximally. So I haven't talked about that. So let's talk about it now. Now suppose that I gave you just a connected graph. Like suppose I even gave you this tree over here. You would agree with me that if I were to look at this, if I excluded in my subgraph one of these vertices, I'd actually be excluding parts of my graph that actually do exist paths to it. Meaning that I could actually extend my graph by at least one edge and at least one vertex, right? So suppose I want to include as much that I can possibly reach from some path between any two pairs of vertices in my subgraph. So I pick some subgraph, and the question is, can I extend the subgraph so it includes more vertices? And if the answer is yes, then it is not a connected component. If I can reach more vertices or across more edges, I include these in this subgraph. And when I cannot no longer include any more vertices or edges, then I could call it a connected component. So just as a quick example, suppose I have the following graph. So notice that if I picked any one of the vertices here, here, or here, notice that if I try to extend my subgraph, say I start off with a subgraph, it's just one isolated vertex. You'll notice that it's not maximal, right? I could perhaps include more vertices and edges. Notice that there's these ones right here. I can extend this. There could be more edges in my subgraph. So notice that I can keep extending out this subgraph until I've included these four vertices. Since these cannot reach these vertices over here, I would call this box right here a connected component. So how many connected components are there in this graph? Well, first, the graph is disconnected, so you know there's at least one connected component, right? If it is connected, and it's just like this tree over here, for example. This is one connected component. That's it. Every connected graph is just one connected component. Yeah, we have three here. We have three connected components. This one, and this one. So the way you can explore or obtain these is suppose you just start at some vertex and you try expanding out your search to see if you can include more edges. And when you can't do that anymore, then you have a connected component. And then you can see if there's more that exist in your graph. Pretty fascinating, right? So this gives you some pretty interesting terminology we can build upon. Pretty cool stuff, right? So, if there's any questions, please don't be shy to ask. I got lots. We went through a lot of stuff here today. So next, what I was thinking of doing, because I'm looking at how much time we have, and I don't want to take too much more of your time, although I could keep going on as long as I would like, but I know that other people have other things to do with their day. Keep in mind, I will cover more on this topic at some point. If you really want me to, let me know. Let me in the comments. Bug me on Patreon. Bug me wherever you want. Bug me on social media. Tell me, Dan, I really like your graph videos. please, I want to see more. Okay. The next thing we're going to be doing, I'll be giving a high-level version of this topic and highlighting a few things. I'll have more details in my notes. Remember, you can get these notes on patreon.com/pagewizard at the appropriate tier. I will make these notes available to you after the session. What we're going to do is we're going to talk about how we can represent a graph on a computer. I'll show you a couple of different ways to do it. These are not all of the ways. There's at least several others. Two others that I usually don't highlight as often, but most certainly do exist. For example, there's a notion of an edge list. There's also the notion of an incidence matrix, or which those are also exist too. But I don't usually talk about those very often. They're very fascinating in their own rights. Especially incidence matrices. If you're ever curious about a topic where you want to know about like the structure of the graph and certain configurations it may have, there's an area called combinatorial design theory, where if you look at the properties of what is called its incidence matrix, there's a lot of people that studied that stuff decades ago. It's pretty interesting stuff. So sometimes people connect this up with experimental design. It's a whole other animal. But yeah, what we're gonna do is we'll talk about. Yeah, I think a perfect place where we're gonna do today is we're gonna talk about how we can represent a graph on a computer, and then we're gonna see one algorithm for exploring a graph. And depending on how far along we get from there, I can take any last questions after that, of course. And of course, what I'll do is I'm actually, one thing I would really like to do is if you have any questions about, say, some other graph algorithms, I could talk about those. But what I think the perfect place for us to stop, given how much time we've got left, keep in mind, I usually like to go for a few hours, so I want to be very careful with my time with you. Then also, although I could just keep going forever and ever and ever, I think I can't remember the longest lecture I've ever given, but I've given lectures that are 4 hours long at least. But my point is I could just keep going. So my point is we're going to talk about graph representations. Then I'm going to show you one algorithm for exploring a graph. And then what we can do is, if we would like to see more about graphs, just please let me know. I'm doing this every week. Let me know. And we can explore some more ways we can explore graphs, and maybe we'll see some more graph algorithms, how we can solve certain graph problems. We'll see some applications of some of these algorithms too. Cool. Okay. Let me just make sure I'm figuring out where we are here. Okay. I always have so many things in front of me. I'm just gonna put this over here. I'm doing a barrier break, okay? Just gonna take a peek at one thing before I get into everything. Excellent. So what I'm going to do now is I'm going to erase the boards. Then we're going to be getting into how we can represent a graph on a computer, so that what you can do is you can start to pick up the stuff that we've been learning, and hoping that maybe you'll get some of the intuition behind how you could represent some of the things we've talked about on a computer. And if you want to try, say for example, applying the algorithm I'm going to teach you here after. So the last thing we're going to do is we're going to explore a graph. So we're going to find out how we can explore a graph. Maybe we'll hold off on its time complexity analysis. But I just mostly want to focus on just getting you something that you can start playing around with if you're curious about it on paper, or something that you could take and pick up and put on a computer if you'd like. Or if you just are curious about it and you want to learn about it. Pretty exciting stuff. But I will include in my notes the analysis, the time complexity analysis. But I'll mention that at the end. I'll give you an intuition behind it. but I'll include it fully, and if people would like me to go through that, I can. Okay, so let me get the thing going. So let's do this. Okay, so the next thing we're going to talk about here are how we can represent a graph on a computer, for example. How we can represent a graph. Now, I'm not going to talk about every way you can do this. There's many such ways of doing them. Some of these aren't even all of them that are out there. I'm going to show you a couple. So I'm going to talk about them in the context of two things. First, I'm going to give you a classic representation. Then I'm also going to give you more of an object-oriented generalized representation. So the reason why I do this is so that you can get an intuition behind what all you need to really represent the graph, versus if you want to add more stuff to represent your graph or adapt your graph to have more of an object-oriented approach to it. Say the vertices represent actual things and you want to have actual parameters or other attributes they may have. This generalized approach is just a simple extension on it. So if you're using an object-oriented programming language, you could pick it up and say, hey, I want this object, this object, this object. How do I represent that with the graph? That's what I want to address. So if you want to just start off with just something as simple as just using arrays or two-dimensional arrays or linked lists, you'll see that all of these elementary representations are easy enough to get a graph. So the first type is the adjacency matrix that I'll talk about here. So adjacency matrix. As the name suggests, it's based on the adjacent relationships between vertices or nodes. So the relationships that are going to be captured are based on adjacency. So what do I mean by this? You can think of it as something as a matrix, which either is a table or a two-dimensional array. It stores zeros and ones, or as I'm going to show you, you can go a little further with this if you like. Zeros and ones, where if I give you a 2D array, Aij, we would say it's 1 in the spot or 0 in the spot. If it's 1, then that means that the edge ij is in the set of edges. 0 if ij is not in the set of edges. So that means that if there's a 1 in this spot in the matrix, that means that that edge exists in the graph. If it's a 0, it is not. So let me do an example here for you. So let's do an example. So suppose I have this matrix, this graph. I'm just going to label all the edges just to help us see what we can do here. So I'm going to V0, V4, V3, V1, and V2. So I'm going to call this one D, going to call that E, going to call this C. I think I've labeled all the edges and vertices. So if we take a look at this, what I'm going to do is I'm going to presume with this representation that vertices are labeled 0 through n-1 if there's n vertices. So it means that in our rows and columns, they'll start off at 0, 0, 1, 2, 3, 4. So there's 5 vertices here, so it starts 0, 1, 2, 3, 4. 0 is for V0, 1 is for V1, 2 is for V2, 3 is for V3, 4 is for V4. Okay? And then naturally, each one of these may be adjacent to another vertex, each respectively labeled as 0 through 4. And now you might ask, Dan, why are you labeling them at 0 through 4? It's because even though you could give these names, like specialized labels, or they may have associated objects with them, You could look at these also as indices, ways you can index into the table or two-dimensional array, matrix, however you'd like to look at it. So for example, if I look at this graph here, do I see an edge from V0 to V0? No. In fact, you could do this with every one of the vertices here. None of them have self-loops. So you know right away the diagonal of this matrix has zeros in it. Now, V0 is not adjacent to V1, so you know it's not there. You can also, by the way, you could also notice that V1 isn't adjacent to V0, so I'm going to just put 0 there too. Okay, V2, now V0 is not adjacent to V2. It's only adjacent to V4, so you know there's just going to be a 1 there. Now next, let's look at V1. V1 is adjacent to V2 and V3. So we have V2, V3. It's not adjacent to V4 though, right? Now, vertex 2. Vertex 2 is adjacent to V1 and V3 of vertex 1, vertex 3. Vertex 1, vertex 3. But it's not adjacent to anything else. Does everybody see that? So now, we've got V3. V3 is adjacent to V2, V1, and V4. V2, V1, V4. It's not adjacent to V... Well, let's think about this. V3... It's not adjacent to V0, sorry. Yes. Now, next we have V4. V4, let's take a look. Well, V4 is adjacent to V0, but it's not adjacent to V1, V2. It's only adjacent to V3. And there's our adjacency matrix. So this matrix tells you if a vertex is adjacent to another vertex. So you can use this information to represent a graph. Because remember, like I told you at the beginning of our lesson, it's fundamentally about the representation of the connections between vertices that really matter here. I must stress that this representation is very easy to augment too. So for example, if you want to have distances, you replace the ones with distances and make everything else like infinity or something. I'll have more discussion about that if we talk about where or if we need what we call weighted graphs. I'll talk about that. So one other thing, I promised you I was going to show you how you can generalize this idea. So what you do is here's like a very object-oriented way you can look at this way of doing things. So what you could do is you still have a two-dimensional array. You still have it where you're indexing like this. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. And now instead of storing zeros, you store null pointers or nil or null. Whatever language you would have for whatever the conception of null might be. It might be 0, literally. So suppose all of these are nulls. So wherever I had a 0 there, I'm going to make that null. So I have null, 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 null. And wherever I don't have a null, I'm going to put I would have a pointer or a reference to the edge object that's associating the two vertices. So what I would do here is if I have my edges, which I've labeled here, suppose that each of these is an edge object. So I want to have an actual object for the edges. I can index into a spot to get that edge object. So for example here, V0, V4, there's A, right? So you could just have a reference or pointer to A. So if ever you need to do anything with the graph, like say these edges represent something for you, you can use it this way. Likewise, you can even have an array just for your vertex objects as well. So if ever you need to do things like marking them or tweaking some input they may have, or attribute. Let me complete this for you. So we would have D, then E, then another null, then you would have D, then you would have, I believe, another null. I guess the whole diagonal would have nulls, right? Because they all have zeros. So you'd have E here, you'd have C, C. By the way I'm filling this in, do you see anything interesting going on with that matrix over there if you've learned a bit about matrices? N, I have a B, I have a B, I have an N, and an N. Is there anything interesting going on here, by the way? Did you see anything interesting going on? What I wanted you to do is look at the diagonal here. So start by looking at the upper triangle, so this side of the matrix. Do you see anything interesting going on with the opposing side? It's like a mirror image of it. So you just take this, go like that, they're the same. Just a mirror of it. You do the same thing with this matrix. With an undirected graph, this matrix will always be what we call symmetric. That means the upper triangle is going to be, in the lower triangle, they're going to match each other like this. In a directed graph, that isn't true though. But like I said, you could represent a directed graph using the same approach as well. Just the matrix won't necessarily be symmetric like this. It's a nice property that also, if you care to optimize this representation, you could just simply get rid of the lower triangle if you're trying to optimize, but you have to keep in mind that then you'll have to make sure you take into account that you have the ordering of the vertices correctly whenever you're indexing into this. So just one other thing you can keep in mind, but you can still use this space. It's probably useful just to use the space if you have it. But that's just the other point of discussion. One thing I want to bring up about this representation, so if you know how to make a 2D array, you know how to represent a graph. Piece of cake, right? So space, this uses big O of n squared space. So notice that the dimensions of this table or matrix or 2D array, it's n by n. So notice that you're going to have big O of n squared space, presuming everything that's being stored in these is some constant amount of space it's being used. So that's one thing you have to keep in mind. So this is appropriate heavily for graphs that are dense, meaning they have many edges in them. So this is, I'll use good in quotation marks. I don't really like talking about good and bad and this kind of stuff. It's more of a trade-off game. It's about pros and cons. So if the graph is dense, meaning it has many edges in it, which this should remind you of something that we talked about earlier on. Do you remember me telling you about the maximum number of edges a simple graph could have? It's the same as this. So the closer your graph becomes to a complete graph, the better this representation will be utilized. Because then notice that if you don't have a dense graph, many of these are going to be 0. And it means you're just wasting space, probably. We really care about the ones. The ones are what really matter. So sometimes even people will optimize this representation into something called a sparse matrix, where you turn this more into a linked-based structure. But I won't talk about that here. The big perk of the adjacency matrix is that if you ever want to check if an edge ij is in the graph, how do you do that? How do you do that? What do you do? You just simply index into the two respective spots, right? If I want to know if vertex, if I want to know there is an edge whose endpoints are I and j, I just look at the matrix, right? So if I want to look for, say, 0, 4, if there's an edge, 0, 4. I go into row 0, go column 4, it's right there, there's a 1. So I know that there is an edge there. In fact, if I use this representation, I can literally get the edge object. But I could do this in big O of 1 time, in constant time. It's very fast. One remark I also want to make, if you're curious about, okay, Dan, I don't really, suppose I have a bunch of objects that actually are trying to access parts of this graph. Well, you can always use a lookup table that will tell you what their number is in here, what some people call a map. And that's a whole other topic for its own right that I do talk about in some of my data structures videos. So these are a couple things to keep in mind when it comes to this. One other detail I really want you to be aware of is if ever you need to get all of the edges that are incident on a vertex, you're going to require big O of n time. You're going to take linear time to do this because you have to access one row of this matrix. You have to read through it. Sometimes there's zeros, sometimes there's ones. To collect those up, you need to go through one of the rows of this matrix. So please keep that in mind. It's actually rather important for the analysis if ever decide you want to use one of these. so that's the adjacency matrix. Piece of cake, right? So the next representation we're going to talk about is the adjacency list. And it attempts to address one of the major issues that we had here. So what we're going to do here is we're going to be looking at if we have an adjacency list. Sorry, I'm not sure if you could hear a phone ringing or not. Usually that's off. There's always some fun things going on over here. But anyways, the next representation we're going to talk about is the adjacency list. Now, the main objective here with the adjacency list is to address this issue that we had over here. So notice that I had a lot of I could potentially have a lot of zeros if my graph is what we call sparse. So meaning that the number of edges is more like big O of n as opposed to big O of n squared. Meaning it's more of a linear number. So it's kind of relative to the number of vertices-ish. It can be off by constant magnitudes, but it won't be. The point is that there might not be as many edges. There's less edges than there are for a really dense graph. So what we're going to have is what we call an incidence sequence. So some people would even call this a collection of incident edges. So in the most purest sense, you'll see that this actually gives you the information about incidence, just akin to whenever I wanted to get the incident edges over there. So it's going to have an incidence sequence for each vertex. Where there is a collection of incident edges for vertex V. So for each one of the vertices, you're going to have a collection of incident edges, which in the adjacency list in its most pure sense will just store all of the adjacent vertices. But very often you'll find that this is actually, well, I mean, it gives you the information as well about incident edges too, which is nice. But you can also have this storing the information of each vertex or the edge objects if you ever need edge objects. So like that, you can also generalize it. So classically, you got to look at it like this. So what I'm going to do is I'm going to use the same graph I had over there, just for the sake of consistency. So I'm going to have V0, V4, V3, V1, and V2. So I'm going to have D, E, C, B, and A. And classically, you'll find that this is represented as follows. 0, 1, 2, 3, 4. What's going to happen is we're going to have an array or a list that is going to contain pointers or references to linked lists. So each one of these is actually going to be the head of a linked list. Each will store the opposing endpoint of each incident edge. So for example, if I look at vertex 0 over here, well, look, there is 4 is one of its neighbors. It's one of the adjacent vertices to V0. Likewise, if I look at V1, notice it's 2 and 3. Likewise, I look at vertex 2, which just has vertex 1 and vertex 3. And naturally, you could keep doing this. So 3, well, if I look at vertex 3, I have 1, vertex 1, vertex 2, and vertex 4. And vertex 4 has 0 and 3. Do you see all I have is just an array or list? Each one stores the head of a linked list. That's all it does. So you can look at the storage of this as just an array of length n, each one with a linked list. So just please keep that in mind. Naturally, you can extend this into a primary data structure that is going to be a list or some data structure that's going to allow you to index in like this, similar to a map. And for each one of those, we'll have a secondary data structure, which could be some collection of incident edges. So this could be a secondary data structure of your choice. So usually, classically, it's just a linked list because specializing it requires you to have more information. This is easy enough to do, but you can always have it where it's a primary structure, where it's like some map, and then you have it where each one of these, once you have the index to get in, you can get the incident edges. And the incident edges are stored in some collection. So that's the adjacency list. It's surprisingly simple as well, as long as you understand that over there you're dealing with a two-dimensional array, here you're dealing with an array, and then you're dealing with each one of these having a linked list. If you know how to implement a 2D array and implement a linked list, you can implement any one of these graphs. Piece of cake, right? So two things I wanted to mention. So the first thing is that we always have these sort of drawbacks to each one. But I really want to point out something that's rather important here. And this actually comes back to our best friend, the handshaking lemma. So how much space does an adjacency list use? Well, it has a reference or pointer for each one of the vertices, right? So you know the amount of space it's going to use is at least n. But what's the length of each one of these linked lists? How many nodes are in each one of these linked lists? I would like to know the answer to this. See, this is where this handshaking lemma is going to be your best friend. So notice, because it's an adjacency list, if you look at our definition here, it's an incidence sequence for each vertex. So if you look at each one of our linked lists, how many nodes will there be in each linked list? The degree. The degree. So notice that the degree, so each one of these, so each list has the degree of some vertex. So like say degree of VI, many nodes. But what is that if I add up all of these? That's the sum of the degrees, right? Over all the vertices. And as we established by the handshaking lemma, this is exactly equal to 2 times m, which this is big O of m. Because it's just 2 times m. M is 2 is a constant. So now the total amount of space to represent this is this array and all of these nodes, presuming that each one of these objects is big O of 1 in its space. So this has a benefit if the m is not close to big O of n squared, right? Otherwise, this just devolves into big O of n squared like we have over there. But either way, these two representations will allow you to represent any one graph. So this is one big perk this has. If you have a sparse graph, so one that is close to big O of n in its edges, or very few edges, this is substantially better in storage than the adjacency matrix is, right? However, it requires a little bit more work for its implementation. The adjacency matrix is much simpler to implement. So that's the first thing. Now, so that's the good news I have for you. Now, if ever I want to find out if a vertex is adjacent to another vertex, well, let's answer that question. How do we know? Like, suppose I want to know if vertex 1 is adjacent to vertex 3. Well, I would have to index into this spot, which this is just an array. I'm going to use the number that corresponds to that vertex to get here. And then I have to navigate this linked list, right? Well, suppose that I access vertex 3 or vertex 1. Either one should be able to tell me, because it's an undirected graph, it doesn't matter which one I use. If I go vertex 1, it'll be able to tell me vertex 3 is adjacent to it by traversing this linked list. But how long can this list be? Well, it's based on the degree of the vertex, right? So if it's a directed graph, you would have to index into the first endpoint to get to the second one. If it exists, it'll tell you yes or no if you traverse through here. Okay? You just go through one by one, traversing a linked list. If you know how to do that, you know how to test for adjacency. So this is going to take... So it's going to be big O of either the sum of the degrees, or more simply, it could just simply be you pick, because all you have to do is you pick one of the two. So it's going to be so it could be the sum of these, it could be the min of the two, it could be the... Keep in mind, you can always have it where you tweak this a little bit. So you could say, okay, well, which one's the shorter of the two? I'll take the shorter of the two. But because keep in mind, if I do access this spot and it's indeed adjacent to the other endpoint, it doesn't matter which of the two you go down. But the point is it depends on the degree of the vertex. That's the point. And the degree... If this is, say, a complete graph, you may have to take, it may take linear time in the worst case. Because what's the degree of any vertex in a complete graph? It's big O of n, because it's n minus 1. So, one thing I wanted to bring up for you, just to kind of cap off this discussion, is why would we care about if a graph is dense, like a complete graph, or sparse, like where it has very few edges, or not as many edges. It's not close to big O of n squared. I thought I would give you an example of a graph that is sparse, and it does occur itself in many applications. There's many kinds of graphs like these. So knowing about the structure of the graph, how many edges does it have, the underlying topology of the graph, like what structure does it have? These are all very important things to investigate if you have a graph that you're using for some application. So I thought I'd give you an example. So the big thing to take away from an adjacency list is if M is big O of n, then this will be quite efficient. Because many of the operations, otherwise it sort of, the edges, because there's so it can have so many of them, it could be the case that this actually starts just becoming no different than what we were dealing with when we started, right? So I thought I'd give you an example of a sparse graph. So something called a planar graph. So this is a graph where there exists a way to embed or draw it in the plane. So when I'm talking about the plane, I'm like talking like a piece of paper like this. So you could draw it on the piece of paper. In the plane. So I'm not talking about like a literal airplane or something. think of this like a piece of paper. I want to draw it here. Such that its edges only cross at their endpoints, so at the vertices. So believe it or not, a lot of different kinds of graphs you encounter in practice actually are this. So I'll give you an example. Actually, I alluded to this one previously. So suppose I give you K4. So here's K4. So here's one possible way I could draw K4 for you. Now, you might say, Dan, does this have any crossings in it? And the answer is yes, it does. It has one, at least one. It's right here. There's a crossing right here. But if you read my definition here very carefully, that doesn't preclude it from being a planar graph. So this is a graph where there exists. That means there's at least one way to embed or draw it in the plane such that its edges only cross at their endpoints, right? Well, that's not a good drawing of this. If you look at this a little more carefully, take this vertex, drag it inside of the triangle like this, and you end up with another drawing I showed you in the past. And this is the same graph. So there's no crossing. This is still K4. So that means that this graph is planar. So K4 is planar. So graphs that are planar actually have very few edges in them. So, for example, we've talked about trees. We know trees have n-1 edges in them, right? So that means that the number of edges is big O of n. There's all sorts of other ones that have very few edges in them. Planar graphs are one of them. So if you encounter a planar graph, the adjacency list representation will be your best friend, because planar graphs also have this property. So if you're wondering where you might run into things like this, if you're dealing with geographical information that's on a flat surface, now keep in mind, real world geography is not flat, right? However, if you're dealing with a simple model where I want to go from A to B, and you want to go there and you have estimates of how long it might take, a lot of that information, presuming that you're not dealing with any weird structural properties that you may have with a highway or anything like that. If you're just dealing with simple little intersections at roads, it's probably planar. So keep that in mind. There's a lot of applications out there for design of circuit boards and all these other things that involve planar graphs. Interesting stuff, right? So that's all I have to say about how we could represent graphs on computers. Excellent. So we're going to do one more thing here with everybody. So I'm going to talk about how we can explore a graph, and that's going to be the last thing we're going to do here today. So I'll show you one algorithm that you're capable of for doing this. And this isn't the only one, but it is one if you want to get started at exploring in graphs. Okay. So before we get into talking about the algorithm we're going to discuss, I'm going to give you the notion of what it means to, what is a graph traversal? Because the goal in a graph traversal is to explore the whole graph. So let me talk about that, and then we're going to talk about our algorithm. So anyways, everybody, what we're going to do is we're going to talk about how we can traverse a graph. So I thought I would get myself into proper attire. So let me just get my explorer hat on. There we go. There we go. We got my hat on. And now we know we're going to go on a journey, okay? So the first thing before we talk about how we can explore a graph is I'm going to talk about what that means. So we're going to talk about a graph traversal first, like what that means. So what's a graph traversal? So many ways to explore a graph are adapted on this idea. So what you do is you have a process of starting at a vertex, u in the set of vertices, and processing all the vertices and edges reachable from U. So I haven't really said what that means yet, so let's talk about this. So there's two things. What does it mean to process a vertex or edge? And what does reachable mean? So in these processes, the way I'm going to adapt this for you is that every time I go to a vertex, I'm going to visit the vertex. Meaning I'm going to do something we could call mark a vertex. We're going to presume that this is capable to be done in big O of 1 time. Meaning I have access to the vertex, so that means I should be able to mark it directly in constant time. Likewise, if I have access to an edge, I'm going to presume I can also label this edge with some label in constant time, because I'll have access to it. So that's what I mean by processing. Our goal is to mark all the vertices and label all the edges. If we can do this, then we've explored the entire graph. And this idea will be a backbone if you want to explore or adapt this searching approach, this traversal idea, to do all sorts of other things like computing pathways in a graph, finding cycles in a graph, counting vertices in a graph, finding the connected components in a graph. So let me draw you a picture just to help kind of motivate what I mean by reachable. Okay, suppose I was given this graph, the one I have right here. So suppose that U is the vertex with an A at it. And naturally, I want to know if U is reachable to all the vertices. So what does reachable mean? As the name suggests, it means that there exists a pathway from U to that vertex. So for example, is G reachable from U? The answer is yes, because there exists a path from G to A, and A is U, right? So I must stress that all the vertices here are reachable from U. If there was a vertex that was not reachable from U, suppose that I have a vertex called I here, we would say that I is not reachable from U because there doesn't exist a pathway from U to that vertex. Likewise, this would also imply there's two connected components, and if I wanted to explore the entirety of the graph, not just what's reachable from U, I would have to start my traversal again at I. So we're going to only focus in on, I gave you a vertex, I would like to process the graph from all vertices and edges that are reachable from U. If ever I wanted to take this process and adapt it further, all I have to do is just apply this again on a vertex that is not marked. Does everybody see that? So if I'm trying to process the entire graph and say there's parts I can't reach, I just simply restart this process again. Just the thing is, I do it on an unmarked vertex, one that has not been marked. So all you have to do is have just a loop. So you can imagine you have to go through each one of the vertices in the graph, You start it up, you just check if it's marked or not. If it's not marked, then you just start this process up. That's the framework we're going to work with. So I must stress that when we do this, the time complexity depends on the representation of the graph. So please keep that in mind. So one of them might force a certain time complexity, another one might degenerate to the same time complexity. So just keep that in mind. So the algorithm we're going to talk about is depth first search here today. So what I wanted you to do, I want to let you use your imagination here. So we're going to use our imagination. We're going to imagine this graph over here was a maze. It's not obviously a very sophisticated maze, but we're just going to imagine it as a maze. And I don't know where I'm going in this maze. I want to explore the maze though. So think of the graph like a maze. A labyrinth, if you'd like. Where the following is going to be the case. So the vertices are going to be the intersections. So so notice that if you look at this more like a maze, if we imagine it like that, you could imagine these being dead ends or where hallways meet each other. So intersections or dead ends. And you can imagine the edges as passages that connect these intersections and dead ends. So the edges are passages. So to help motivate how depth first search is going to process this graph, all the stuff that's reachable from our starting vertex. So we have a starting vertex will be given, and I would like to explore or process this graph. So I want to mark all the vertices and edges that are for our graph here. So anyways, so to explain the idea of depth first search, I wanted to use this idea of trying to seek things out in a maze. So to do this, I'm going to explain this. Sorry, I'm getting really excited here. So to talk about depth first search, now that we can imagine this like a maze, what I want to do is tell you a story, and this story I'm hoping will help motivate how we're going to process the graph, specifically all the stuff in our graph, the edges and vertices reachable from a start vertex. So this comes back to the myth of Theseus and the Minotaur. So in the story, there was this king, the king of Crete, King Minos. He was sort of in a situation where he was given an offering to sacrifice a bull. Well, sorry, it was a white cow. Sorry, no, it was a white bull. White bull. I gotta get these things right. So it was a white bull, and he refused to do the deed. And this is sort of just how a common theme in a lot of Greek stories. Naturally, when you don't do something a god would like you to do, something funny happens, and funny that happens with it. So, kind of coming back to this, what happened was sorry, I'm getting so excited here. I'm going to tell you the story right from the top here and why we're going to really care about this. Sorry, I'm just getting so excited. So in the story of Theseus and the Minotaur, the main character Theseus is tasked with stopping this beast called the Minotaur. So the Minotaur lives in the labyrinth, this incredibly complicated maze created by Daedalus, the great inventor in Greek mythology. So Daedalus had crafted this maze so complicated that anybody that goes into it, they get lost. And this great beast, the Minotaur, half man, half bull, was being offered sacrifice, well, basically offerings from Athens with respect to some previous affair that I'm not going to go too much into detail about here. But you might ask, Dan, why is there a half-man, half-bull sitting in this labyrinth? Well, I'll tell you a little bit of the backstory. Okay, so the father of, well, the father, I guess technically I would say sorry, I'm getting a little ahead of myself. There was a point where King Minos was supposed to sacrifice a white bull on behalf for, I believe it was Poseidon, if my memory serves me correctly. Now, he chose not to because it was this wonderful white bull. So, as punishment for not doing this, what happened was Poseidon had basically made his wife fall in love with the white bull. Don't ask me the details of how this works. And what happened was, I'm not even kidding, like you could find interpretations with this, like where there's literally a wood-crafted bull that's crafted where King Minos' wife, the queen, would go into the wood-crafted bull and the white bull would do the thing. And we're not going to talk too much about that, but the point is it created the Minotaur. And Theseus is coming into the labyrinth with the help of King Minos' daughter, who's technically, I guess, a sibling of the Minotaur, to slay the beast. And Ariadne had given Theseus a very large spool of thread. So in the story, the way this worked is that Theseus would travel and explore in the labyrinth with the spool of thread at the entrance of the labyrinth. So Theseus would begin at U, and as Theseus would explore, Theseus would use this thread to help navigate so Theseus would not get lost in the deep, complicated labyrinth. So that Theseus could explore the labyrinth, come across this great beast, half man, half bull, and challenge it. But the point is that Theseus had to explore the labyrinth to do this. So the way this works is that Theseus could begin at the start of this, say, starting at U, and would begin to start going down one of these tunnels, these passages. So Theseus would bring that string down perhaps to H. Now, on the way there, notice that I have not labeled this edge at all. So Theseus has not gone down this edge at all. So maybe Theseus should label this and say, hey, look, I've gone down this passage. And then upon reaching the opposing side, notice that Theseus isn't going to mark an X or anything there. So what I'm going to do is I'm going to mark an X, and I go and look, see if there's any edges or passages I have not yet explored. But if ever I run out of options, I can roll back up my thread to go back to where I came from. So this is the great trickery and the great mastery of using this approach if ever you're in a deep, complicated place like a labyrinth with a half man, half bull, and you need to find your way around and explore without getting lost. Is if ever you're lost, you unwind or wind up the thread to continue your exploration. Because if you have this sitting right at the beginning, there's no way you're going to lose track of the entrance, which naturally would get you back to where you started. So let's continue this process. So naturally, if you think about it, I could just simply go, now I've done this, so I'm going to roll up my thread. So I'm going to roll this back up to where I started. So I, as Theseus, I notice that there is this passage here that I have not yet explored. I'm going to label that with this green here. And then I reach this vertex. Notice it's not marked. So now I'm going to explore. And now I'm going to pick one of the passageways to go down. Notice that both of them I have not yet explored yet. So I'm going to take my thread and I'm going to go down this way. I'm going to now mark this vertex because I'm going to explore now this point. I'm going to continue. Notice that I have one incident edge I have not yet explored. I'm going to go here. I'm going to start by marking over here and I'm going to continue this process. So every single time I get to the next vertex, and I have not gone down this way before. Do you notice every time I'm just going to mark where I was? Every time I do this, I'm going to roll out more of my thread. And if I run out of options, I'm going to start winding this back up and go backwards. So notice I'm going to process each vertex as I encounter them. But notice that I do it after I've considered an edge that I have not yet done an exploration on. So notice that I could just continue this process. So I can continue, maybe I'll go this way now. And now I'm going to explore from here. I could go this way. I could go here. Perhaps, maybe even there's the Minotaur there. Who knows? Who knows? But here's the point. I need to process all of the edges and vertices that are reachable from this vertex. But notice that this edge here, notice the opposing endpoint. I already put an X there, right? I already marked it. So what I'm going to do is I'm not going to go down that way. Instead, I'm just going to label this edge in red instead. And say, nah, I've already been down over there. I'm not going to do that. So what did I tell you to do if we run out of options then? So I'm not going to go down that way because I may go back a way that I used to. I may have more things to explore. What did I do? Well, whenever I had an option, I roll this out, right? Whenever I run out of options, I wind this up. Right? So instead of going down this way, because I know this goes somewhere I've already been, there's no point in going that direction. Or perhaps it's a shortcut back to the entrance, but most certainly I'm not done at this vertex until I've examined every one of the incident edges. But now I have no more options, so I'm going to go back this way. I check the same thing. Notice there's no more options, so I'm going to go back. Oh, I have this edge here. Well, notice here that the opposing passageway, when I'm right here, notice that I've already been there. So I'm just going to label this in red instead. I'm not going to go that way because there might be more for me to explore. For example, maybe there was another incident edge here that I haven't yet seen. So now I'm going to go back here. No more options, no more options, no more options. I'm keep winding up my string until I get back to the entrance. And I'm back at the entrance. I have to have had to explore everything if there's no more options at my starting point. So there could have been another incident edge to explore, for example, but there's no more. But now notice at the end of this process, every one of the vertices was marked that's reachable from you, and all of the edges were labeled. Now notice that, so I want to give these names. So these red edges are what we call back edges. So they serve an actual special purpose that I'm not going to talk about here today, but most certainly I will talk about it at some point. Then the green edges, these are called forward or discovery edges. Forward or discovery edges. So you might ask, Dan, why are they called this? Okay, so the discovery edge means that I've discovered a new vertex, right? I'm going forward in my search. A back edge means, oh, I would have to go, I'm going back somewhere I've already been. Okay, so this will allow me to process it. And this is the idea of depth first search. So if you understand this idea, you understand depth first search. Now, one thing I did not show you that I believe it's a good idea I show you is that actually this thread that we've seen, this string, as in the story, it isn't just some fictitious thing. Like, it isn't literally a string like this, but it's actually a stack. It's actually a stack, whether it be a recursive approach of using the call stack, or it's actually a data structure, a stack. So when we explored this, what we actually had was a stack. So what we did, we start off at U, which was A. We went to H, right? That was the first thing we did. But I finished at H after I processed out all the incident edges at H. So I was down there and I'm back at the top of the stack. This is the same thing, by the way. It's us unwinding. So I'm going back. So whenever I have a new option, I place that onto the stack, I mark that vertex, then I start examining the incident edges. So next, I went to B, I examined my incident edges, I went to C next, right? And then I went to D, then I went to E, and then I went to F, and then I went to G. Do you see how the string actually corresponds? So the idea here with the string actually corresponds to how you would read the stack from top to bottom. The top of the stack tells you where you currently are, and if you were to roll back the string, ignoring anything that we finished processing like H over here, this is not a part of the stack anymore. It's just visualized there for you. If you were to wind up back up the string, it's equivalent to me popping this stack. Popping the stack, by the way, if this is a call stack, like your function calls, this would be no different than if every time you finish calling our explore or traversal at a given vertex, whenever that finishes, we go back to the vertex that was the one directly below it by popping the stack, which is the same thing. So hopefully this demystifies this. So when I finished G, I went back to F, right? When I went back to F, I went back to E because I had no more options again, right? Then after D, I ran out of options, C out of options, B I was out of options, and I got back to A and I finished. So you're going to see how I'm going to describe depth first search to you is going to be using this idea that notice every single time I mark the vertex I'm currently at, and then I examine all of the unlabeled edges incident on myself, on my vertex. If I run into a place where I'm going to have a new vertex to explore, as would be the case at a discovery edge, I then proceed to do a recursive call, pushing a new call of DFS, what we would call DFS, it's on that vertex. And we repeat this process. Now keep in mind, you can always get rid of the recursion, but I think it's nice and easy to describe this way, recursively. And it's all based on this idea. So hopefully you find that kind of interesting. So I'll have a bit more details in the notes, but let me describe the algorithm to you now. So here's the algorithm. So we have DFS, we have some starting vertex. Now I must stress that if the graph is connected, then you can ensure that this entire graph gets visited by DFS. I hope you can see that from this process because we exhaustively explored the entire graph. However, if it isn't connected, then you know that you're going to probably have to run this again on another unmarked vertex, which as I talked about earlier. So I have a vertex U and V, and I'm going to presume it's connected, but it doesn't have to be. It's only if you want this to explore the whole graph that it needs to be connected. So we're going to presume it's connected. And as output, now it's not really going to give us output per se. The way I'm going to describe this to you is it's actually going to make modifications to vertex objects or an array that represents the vertices and labels on edges. So this could be another array of edges, or you may have vertex objects and edge objects akin to what I talked about when I was talking about representing our graph previously. So this is going to be a DFS traversal of G starting at U. So what was the first thing we always did? We mark the vertex. That was the first thing we do. So we mark U. And then I'm going to do is I'm going to go through every edge that's incident on my vertex. So for every edge UV, so I'm going to go on all of the incident edges. So remember, this is the first endpoint, so you're going to have to go over each one of its incident edges. And we already talked already about how you can do this with two different representations. So for example, in the adjacency matrix, you'd go through one row of the adjacency matrix in the adjacency list, you would index into the appropriate list, and you would traverse that linked list. For example, if we're at least thinking about this classically. So for every one of the edges, you're going to do as follows. So if it's unlabeled, so if the edge is not labeled, because we care about the ones that are not labeled. Then we check if it's marked. We check if V is marked, because we don't care about if it's already labeled. It means we don't have to visit it again. We don't have to do anything with that edge. It's done. It's already been processed. So if V, the opposing endpoint, is marked, then what did we do? If I run into another endpoint, so if I'm Theseus and I'm going to explore and I see that the other endpoint is already marked, is it a forward edge or a back edge that I would be using here? Well, surely I've already been there, right? So it means it's going to be a back edge. It means there's nothing there to expand on my exploration. Then we're going to label UV as a back edge. Otherwise, the other possibility now is that we have a discovery or forward edge. So we're going to label UV as a discovery edge, because we've discovered a new vertex. And then naturally we go there, right? We go there. So I'm going to call recursively DFS on V. And that closes that else block. This closes the if statement, and then this closes the for loop. And that is DFS. So notice that it is exactly what I just described to you earlier. And I must stress that you can reframe this into an iterative algorithm. The difference is that you're going to see that you might want to have your own stack instead of just being the call stack if that's the case. So that's DFS. I'm going to make a couple remarks here, and then I think this will be a good thing for us to talk about maybe in the future. So let's talk about the time complexity. So that's the first kind of big thing. So the first thing you should notice is marking. I could do that in constant time, right? All of this in here, if I ignore the recursion first, all of this I can do in constant time. So naturally this becomes a game of, okay, so that takes constant time for every edge. So I have to go through all the incident edges. So there's kind of three big pieces here. This takes constant time. If I ignore the recursion, this takes big O of 1 time, some constant amount of time, or constant number of operations. This is ignoring the recursion. So that's ignoring the recursion. And this depends on the computation of the incident edges. So this is the time complexity for incident edges. So if I need to get the incident edges, you need to know that, because how many times this for loop happens depends on the number of incident edges. So you have these three pieces. So first, if we ignore the recursion, we have it where, okay, so there we have this. Computing the incident edges. So we know if we have an adjacency matrix, computing the incident edges takes linear time in the worst case. You have to examine all of the edges, potentially in a row of the adjacency matrix, right? Right? So you know it's going to be big O of 1, n, and some constant number of operations, right? That's for one call. But do you see that I never call DFS on the same vertex twice? I never do that. I only do it when I encounter an unmarked vertex. So the way you got to look at this is, as I'm exploring this graph, every time I mark a vertex, it goes in this bin. I never go back into this and start pulling them out. Whenever I mark a vertex, it goes in the bin. But I only touch each one once. Likewise, if ever the vertex is unlabeled, I only do something with it once, right? But in particular, I may revisit an edge again, but just another time, but it won't be the case that I'll have to label it again. It only gets labeled once. The vertices only get marked once. So just please keep this in mind, because when I explore, I always call DFS on an unmarked vertex. But how many can there be in the worst case? how many can there be? So I have some constant amount of time plus some constant times n, but I do this for each vertex, right? So that means that, but how many vertices are there? Well, there's n, right? So this is going to be for an adjacency matrix, connect big O of n squared time. Okay, how about the adjacency list? But I must stress, remember, that the number of edges can be no more than n squared, big O. Sorry, I'm getting very excited here. So big O of n squared, the number of edges can never exceed that. So if you have a dense graph, like this is actually not bad at all. An adjacency list, however, let's think about it. So you mark the vertex, takes constant time. This over here, computing the incident edges, how long does that take? So I'm going to label these as like 1, 2, and 3. So 1, we have the incident edges, and then we have all of this stuff. Okay, we know that's taking constant amount of time. So C1, many operations, if I call it C1, plus we have some constant number of operations times the incident edges computation. But we know to compute the incident edges depends on the degree of that vertex. So in this case, it would be the degree of u, right? So whatever u is, the degree of that tells me how long it's going to take me to compute the incident edges, right? Because I have to go through that certain. Sorry, I get very excited here. To do that, I have to go through the linked list, and how many nodes are in the linked list, the degree of that vertex. But I do this for all of the vertices, right? Just by the same reasoning I talked about here. I never mark a vertex twice. So I do this for all the vertices. So I do this for each vertex. Now here, this is our best friend pops up again. So we have a sum over this. So some constant times n, right? That's okay. That's just linear in n. So it's just n times a constant plus another constant times the degree of u. But here's the thing. It's C2 times the sum of all of the degrees again. But what is that? What's our best friend? The handshaking lemma. The handshaking lemma would tell you right away that if you actually play this out, you'll end up getting big O of n plus m. Because this right here, when you sum over all of the vertices for each one, you end up with twice the number of edges, which is just 2 times m. So you have n plus m in terms of big O. Fascinating stuff, right? So this is linear in the size of the graph. So that's DFS, everybody. Pretty fascinating stuff. But yeah, so that's how you can explore a graph. And of course, if you ever want to, say, use this again, like say if you want to explore the entire graph, say you have multiple connected components, all you have to do is you just have, so what you do, and I have more details about this in the notes, is all you do is you just go through each one of the vertices. So you have a for loop, and you check if the vertex is marked. If it's not marked, then you run this algorithm. You just apply this algorithm. When you're done, you just continue through your loop, examining each vertex. If it's not marked again, you start it up again. It still will have these same time complexities overall, the entire processing of the graph. You might ask why. It's because we never re-explore the same parts of the graph ever again, right? If I consider one connected component, none of my other traversals are going to affect that connected component, right? They'll just be a part of another connected component. So with more delicate analysis, you can actually show that when you apply that approach, that you still get these same time complexities because they essentially don't affect each other. There's no overlapping computation on the processing of the graph. And then on top of that, the great thing is that the loop itself, it's just, okay, well, I do it each n times, but I don't repeat it, right? So I'm really just, instead of it being like a loop where you go through and you have like n times that, it's really just a collection of each one of your calls on DFS. None of them overlap each other. But yeah, you can use the same approach, the one I just described here, to compute the connected components. But yeah, no, are there any questions? please don't be shy. I'm happy to answer any questions. But yeah, no, it seems like we don't have any questions today. It's a rather quiet day today. I know we had some people popping on in, but I don't mind. I'm always having a good time. So, that being said, I guess we're going to stop here. If you really like learning about graph algorithms, let me know. I could talk more about DFS and some other graph traversal algorithms and some other graph problems. I plan to do this in the future regardless, but I know if you really like graphs like I do, definitely let me know, okay? So that being said, I'm going to say thank you very much for everybody coming on out. If you like what you've seen, make sure you tell your friends to come on out. Be sure to subscribe and follow, and of course, let people know where to find this stuff. It's kind of hard to find it if you don't know about it. So I'll say thank you so much, everybody, and have yourself a beautiful day. I'll see you later.